Hi everybody, and welcome to CARDIS 2021. I would like to welcome everybody both here on site and online via YouTube. Yes, so our first session will be a joint session between CARDIS and the NESI Fall School on Nanoelectronics for Secure Systems. From CARDIS side, this is also special CARDIS. It's the 20th CARDIS. So we have the 20th CARDIS conference this year. It's also a first. So it's the first time we will be having a hybrid CARDIS. So with participants here in the room and with participants online. So registered are 35 participants online roughly. Number is still changing, I guess. And 80 participants here in Lübeck in the Radisson Hotel. So what can you expect? So we will have 3 keynote presentations. All will be here on site. We'll have 5 technical sessions, of which 2 will be online, and the other 3 will be with presenters here in the room as well. For the ones that are actually here in presence, we will also have a conference dinner tonight, and we will have a social dinner, a social event tomorrow in the morning. For people attending online, the way to follow the presentations and talks is via YouTube. So we are hopefully live on YouTube, and you should be able to hear this over YouTube as well. So just follow that link. If you want to participate, ask questions, interact with other people at the conference, especially also online participants, please use our CARDIS chat system. It's a MetaMost system, and you should have received your login credentials with the registration information. There are special channels for each session and each keynote. So if you want to discuss or ask questions, please put your questions into the system there. For participants that are on site here, you can of course ask questions after the presentations. Please keep in mind that we have people attending online, so people will come around with a microphone. So please wait with asking the question until you have a microphone so that online participants can also hear you. Once you have entered the room, you have been checked, you have been either tested, vaccinated, or recovered. So you can move around here without a mask and interact without a mask. So that's how the conference will work. Then if you want to explore Lübeck, you will also have a chance during the social event tomorrow morning. In addition, I just wanted to quickly point out where we are. Actually, I can do that with the button click here. We are right here between the train station where many of you arrived and the historic old town of Lübeck, which is a UNESCO World Cultural Heritage. So there's a lot of nice places to visit, historic places, nice houses and so on. You can visit. There's also a few shops. Lübeck is known for marzipan. You should check that out definitely. And there's also a few bars and so on in the city center. There's one famous historic building is the Holsten Gate, for example, the city council building and so on. So please try to get some time to also explore the city, especially since the weather still is quite stable at the moment. So with that, if there are any further questions during the conference, please do not hesitate to contact us, the organizers. Besides myself, there's Tore here, Alexander, Espanja is also here, and you see a few more people at the welcome desk. If there are any questions, do not hesitate to contact us. And now I would like to pass the word over to our program chairs, Vincent Grosson and Thomas Pöppelmann, who will guide you through our program. So please enjoy CARDIS 2021. That's what we want to do. Yes. Yeah. So it's Control L, not Windows L, right? Yes. I'm sorry about that.
Okay, so thank you. We are really happy to be here in Lübeck with Thomas. And yes, as you know, as Thomas already said, it's an hybrid conference, so that it's some kind of new for us. So after the conference, we would ask you to provide us some feedback via email. We will send some form. If you can provide us some feedback, it could be helpful for maybe for the conferences. And for this one, so for this year, we have 3 technical sessions in Lübeck. So for the presenter, please, during the break before your session, please adapt your slide on the PC and introduce yourself to your session chair. For the technical session that I have live stream, please, so you have received a link to websites for people that will present. Of course, participants will just have the YouTube links, and then to avoid any tech problem, please do it a bit before the session starts. For questions in the room, we have the microphone that will be passed to the participant, and for online, you can ask the Matamos. And then I will talk more about the program. So this year we have 32 submissions, and one was reached one. And among all these 32 submissions, 16 was accepted paper. So quick mark is 0.5 acceptance rate. And each paper received at least 3 reviews, and there is a lot of discussion to decide which paper was accepted. And this is done thanks to the help of the program committees, that the names are listed here, and some sub-reviewers. And if you count the number of people, you see that there is 31 members. So if you have math before 32 paper minus 1, 31 members, 3 review per paper, 3 paper per members, should do the math. And then I will let Thomas.
Yeah, and then in addition, we also have the Best Student Paper Award, because we want to encourage also students to submit to CARDIS. And I think this CARDIS, together with the NESI Fall School, is a good opportunity for students to meet and to discuss their work. Papers that were eligible were papers that were authored by a main author who's currently enrolled as a master or PhD student at the university. So these papers were eligible. And then in the end, by a vote of the CARDIS program committee, the Best Student Paper Award goes to the paper In-Depth Analysis of Side Channel Countermeasures for Crystal Skybar Message Encoding on ARM Cortex-M4 by Hauke Malke Steffen, Lucy Joanna Kohlheide, and Timo Bartkewitz. And I would like you to give them an applause. So yeah, very good work. And this paper will also be presented in the first technical session. And we also have invited speakers. So the next item in the program is a talk by Nele Mentens on the security challenges and opportunities in emerging device technologies, a case study on flexible electronics. And then we will also have a talk by Christine van Vredendahl on challenges of post-quantum cryptography in the embedded world, and a talk by Axel Poschmann on lessons learned for securing the supply chain of a high security smartphone. And with this, we are done with our introduction, and thanks a lot for being here. And then we can start with the next invited talk. Thank you.
And our joint NESI CARDIS keynote will be given by Professor Nele Mentens. She's a professor at KU Leuven and Leiden University. She's a very distinguished researcher, has published over 100 papers, is involved in many research projects, and also involved in many in program committees. For example, she was a program chair of CARDIS last year, CARDIS 2020. So I'm very happy to welcome her at CARDIS in presence this year. So that's really great. We already heard the title of her presentation, Security in Emerging Technologies, where she will give us an overview of what to pay attention to when bringing security into new technologies, some of the minimum requirements and things like that. And without further ado, I'm very happy to welcome you here. Thank you so much for coming. And
Okay, so thanks for the introduction, and also thank you for the invitation, Thomas, Ilya, François, and other Thomas. I'm very happy to be here. So indeed, this talk will be on security and emerging technologies, and I will use flexible electronics as a case study. This should also work. Yeah. So this is the outline of the talk. So first, I will explain what I mean with emerging technologies. Then I'll say something about like minimal hardware security requirements when we want to bring these technologies into products, into deployment, into commercial products. And then I'll mainly focus on one case study, which is flexible electronics on plastics or on plastic substrates. And in the end, I'll say something to summarize which hardware security research has been done already in other emerging technologies. And I know there's some people in the room here who have worked on some of these other emerging technologies. So maybe my overview is not complete, but then I'm sure that it can be completed. Yeah. So first, what do we mean with emerging technologies? So there is a group of researchers or representatives, actually, of industry working on technology, so chip technology, who annually prepare a roadmap or a report on devices and systems. And this is called the International Roadmap for Devices and Systems, the IRDS. Actually, this is the successor of the ITRS that you might know. And this group actually predicts the evolution of electronic devices and systems. And this goes towards the direction of deep submicron technologies, like how far can we go, how small can everything get. But on the other hand, also it mentions devices and systems that do not rely on traditional silicon technology. So there's also predictions on which new technologies will arise. And there's an annual report published, and there's actually different international focus teams that publish different reports. So here are some examples of emerging technologies that I will also mention at the end of the talk, where some hardware security research has already been done. One is the case study that I will use, and that we worked on actually, and that's electronics on flexible plastic foil. And this was covered in the international focus team on More Than More. So how to do other things than just following Moore's law. Then memristors, which was covered in the international focus team on Beyond CMOS. And then also ultra-low leakage technologies, like fully depleted silicon on insulator technology, for example, which was covered in the More report. And actually, the IRDS also emphasizes that security is an important problem. Or an important requirement for these technologies if we want to bring them to the market. So then, next question is, which hardware security requirements or minimal hardware security requirements do we need to take into account before deploying devices that rely on these technologies? And I would like to start with a very simple example. So this is a simple example of a very lightweight or super simple authentication protocol. So what do we have? We have a lightweight device, for example, an RFID or an NFC tag with a cryptographic key stored or generated on the tag. And there's a reader device that wants to read out data from this tag. We assume that symmetric key cryptography is used here and that the reader holds the same key as the tag. I'm also assuming here that it's a passive tag, that it's powered by the reader, and that, of course, data exchange can occur. Then what would this simple protocol look like? Let's first have a look at that and then see what we need in hardware to be able to accomplish this. So the simple protocol could look like this. So the reader wants to authenticate itself to the tag. So to do that, the tag generates a nonce, RA, and sends it to the reader. You can see it here. Then the reader does a computation on this nonce, and this computation should be some kind of pseudo-random function, PRF. The pseudo-random function can be an encryption algorithm or a MAC or anything that should be computed with this key that is stored on the tag already, so PRFK. And it computes that on the nonce. It gets a result, sends it back to the flexible tag, and then the flexible tag computes the same PRF and verifies if the result is the same, and if it's the same, then the reader is authenticated. So this is super simple. But the question is now, what do we need in terms of hardware security to make sure that this can work? So first of all, what do we need to protect against a remote adversary? An adversary that can monitor the channel in between the tag and the reader. We need to be able to store the key on the tag. We need to be able to generate a nonce on the tag, and we need to be able to do some digital crypto on the tag. So those are 3 requirements. We could also look at, of course, and I think there's many papers here also in the conference on that topic, what could a physical adversary do? Of course, we need additional protection then against physical attacks, IP theft, key theft. Actually, these 2 are a bit related to secure key storage and key theft. But these are the things that we all need to foresee on this small tag. So then, if we take these requirements into account and we look at our case study, flexible electronics on plastics, then I can give you an overview of what has been done and which challenges are still open in terms of these hardware requirements that I just showed you. And then in the end, after looking at this case study, I'll get back to the memristors and the other flexible electronics technologies and the ultra-low leakage technologies to give a brief overview of what has been done there in terms of these minimal hardware requirements. But first, let's have a look at our case study, which is flexible electronics on plastic substrates. Before diving into the hardware security requirements, I'd like to give a short intro to the technology. So this technology of flexible electronics on plastics has been used commercially in flexible displays. Actually, it has been used very widely already in commercial applications. So these displays, they consist of millions of thin film transistors, and these transistors control the current through the pixels in the display. So here, this technology is very well adopted for this application. But then, 5 to 10 years ago, researchers, so you can see, so 5 to 10 years ago, researchers discovered that you can also build digital circuits in this technology. So the technology is already widespread used, like with millions of transistors in these displays. But only 5 to 10 years ago, people started looking into digital circuits also. And there have been some examples, actually, of passive RFID and NFC chips integrated in plastics or in paper. Because the chips that are made are flexible and can easily be integrated into these kinds of applications. So this gives like a lot of opportunities for flexible labels, for example, on a bottle, intelligent packages, smart blisters that tell you when to take your pills, electronic medical patches, etc. And if we look at which circuits have already been fabricated and also published, then there was an NFC transponder, an 8-bit microprocessor with a limited instruction set. Actually, there will be a publication at ISSCC 2022 now on another microprocessor with already a more extended instruction set. So technology is moving, and more transistors can be integrated into these chips. Then if we look at the yeah, I will only use this slide to go a bit deeper into technology, but I'll stay at higher level for the next slides. So if we look at the technology, then actually what can you do in flexible electronics on plastic substrates? There exist different technologies actually, but this is the one that we used, and it gives the best combination of high performance and low processing cost. And the technology that we use is based on amorphous metal oxide thin film transistors. You can see a cross section here. So this is the transistor, where the source, the drain, and the gate, and actually also all the interconnection layers are made of molybdenum. Then the gate dielectric is silicon dioxide, and the semiconductor is AXO, amorphous indium gallium zinc oxide. And then this all is deposited on a plastic substrate. So why would we use this technology? I already said, like, you can integrate these chips in plastic or in paper. They are bendable, so that's one advantage. But there's other advantages. And actually, there's also a lot of disadvantages. So we have to look at the application to see if this technology is useful or not for the application or the product that we intend to build. So this is an overview. It's a comparison with silicon transistors. On the left, you can see some ballpark numbers for silicon chips in 10 nanometer. In the middle, you can see the technology that we use for our case study. And on the right, you can see the new generation of AXO technology, which is actually also starting to be used commercially. So there's a company to which you can really produce these chips now. When we did our case study, everything was done in-house at IMEC, actually. So technology is evolving rapidly. So what do we see? First, there's the core supply voltage. And you can see that that is a lot higher for flexible electronics on plastics than for silicon chips, which means, among others, that these chips will have a much higher power consumption. So that's a disadvantage. Another disadvantage is the performance, because if we look at the charge carrier mobility, how fast the charge carriers go through the transistor, then this is also a lot higher in silicon technology than in the technology that we use. So this has an influence on the performance. Then transistor density, how many transistors can you put per square millimeter or square centimeter? You can also see a big difference, but also already an improvement between the technology that we use and the new technology. But this also means that for the same functionality, you need a much larger area than silicon chips. Then if we look at the semiconductor types that are possible, in silicon you have N-type and P-type, NMOS, PMOS transistors. In the technology that we use, the specific technology that we use, the AXO technology, we can only use N-type transistors, which means that we have to use unipolar logic, which is less reliable than CMOS logic. And this also, again, has an influence on how many transistors we can have and how reliable the chip is. So all disadvantages. But luckily, there's also advantages. And for some applications, these advantages are much more important than the disadvantages. So one, I already said, the chips are bendable, stretchable. Actually, in a discussion that I just had with Maddie, there's one more advantage, actually, and that's biocompatibility. So this has a lot more opportunities, actually, in that sense. But there's another thing, and that's the cost. So chips in this technology are typically much cheaper than silicon chips. And that has to do with the temperature at which the chips are fabricated. So there's a large difference in the temperature that is needed for the fabrication. I mean, that's one of the factors that plays a role there. So a lot of disadvantages, a few advantages, but for some applications, these are the things that we need, and these things are less important. So for those applications, it is worthwhile to look into this technology and to see which kind of products could be brought to the market. So if you think back of our very simple authentication protocol, then now we assume that this flexible NFC or RFID tag is a flexible, that it is a flexible tag on a plastic substrate. So then the next thing is to have a look at what we can do there for security. But first, I want to say something about memory also, because now I showed you what, I showed you what a transistor looks like, and I said something about which digital circuits have already been implemented, and about disadvantages and advantages. But another important thing is also non-volatile memory, because if you want to make, for example, this NFC RFID tag, then you need to store the key somewhere. So what are the options for non-volatile memory in this technology? So we need non-volatile memory to store, for example, the cryptographic key after fabrication. So first we make like 1 million of the same chips, and afterwards we need to program the key in some way into these chips. In this technology, electrically readable and writable non-volatile memory, like flash, does not exist. So that we cannot use. The only thing that we can do is use one-time programmable storage mechanisms. One option is to use ink to connect wires to each other, and another option is to use a laser to cut wires. So, for example, if we want to use this first method, then we could connect each key bit to the ground supply and the power supply, so to logical 0 and 1, through a structure like this, like an interdigitated finger structure, which doesn't make a connection if you don't do anything, but if you put a drop of ink on it, then it will make a connection. So if you do this, then the key bit becomes 1. If you do this, then the key bit becomes 0. So before programming, all key bits are floating nodes. Another option, the modificative method with laser, there you connect each key bit to the 0 and the 1 at the same time. And before turning on the power supply, because otherwise you have a problem, you cut one of these 2 wires. So if we cut this wire with with a laser, then the key bit becomes 1, and otherwise the key bit becomes 0. So these are the simple methods that exist, and that's the only thing we have actually for key programming. But I'll show you later that we also have a better method now. So we know now what the technology looks like. We know what the non-volatile memory options that we have. Now it's time to go back to this. So in this technology, how can we make sure that we fulfill all these minimal hardware requirements? And actually, I will not talk about the blue thing here. So yeah, maybe briefly a bit about key theft, but not about physical attacks. So that's something that's still open. First thing is the tag needs to be able to compute this pseudo-random function, like an encryption algorithm or a MAC or something, with the secret key that is stored on the tag. So we need a digital crypto circuit. What did we do? So these are our design choices to implement this crypto circuit. First of all, we had to select an algorithm. At the time we were doing this research, the maximum number of transistors that were reported in this technology in digital circuits was less than 4,000 transistors. So we had to pick something super small to make sure that it worked. So we chose the Catan 1032 algorithm, and cryptographers in the room will immediately say that it might not be secure enough, but this was our first attempt to make at least something work. So block size is only 32 bits. We have a key size of 80 bits. That's still okay, I guess. And in this algorithm, the key is burned into the device, so you don't have a key schedule that every time updates the key, but the key can just be burned into the device, and all subkeys are directly derived from that key. Yeah, so the algorithm consists of a few shift registers and some logic gates. Then the architecture, we didn't have a lot of input-output nodes available, so we made a serial architecture where plain text is entered bit per bit into the encryption algorithm, and ciphertext comes out bit per bit. And then there's this key schedule, the key schedule here on top, where you have the fixed burned key that is burned into the device, which generates in every clock cycle a new KA and KB that are then fed into the here KA and here KB fed into the encryption algorithm. Then like I said, we only have N-type transistors, or thin film transistors, TFTs, which means we have to use something else than CMOS logic. So in this case, and what is typically done in this technology is that pseudo-CMOS logic is used. And this is what a gate looks like in pseudo-CMOS logic. So we have the pull-down network that is repeated twice. And then we have like two steps, actually, where the supply voltage is used in the second step, and a bias voltage is used in the first step. And this bias voltage should be at least 2 times the threshold. Sorry, wrong button. This bias voltage should be at least 2 times the threshold voltage higher than VDD, because you lose 1 VT here and you lose 1 VT here. So just to make sure that the output is still rail to rail, we have to do it like this. So we need 2 supply voltages, actually, V bias and VDD. And in this case, yeah, to make one NAND gate in CMOS technology would be 4 transistors, like 2 PMOS, 2 NMOS. And in this technology, we need 6 TFTs, N-type. And then this I already said, at the lowest layer, this is the AXO TFT that we use in this technology. So then if we look at the results, this was our digital circuit. It's super large because it's 20 millimeter by 20 millimeter almost, so a lot larger than, for a very small crypto algorithm only, a lot larger than what you would expect or than what you get in silicon technology. We had around 4,000 transistors. Yeah, and then at the bottom you can see the 80-bit key that was burned into the device, and sorry, at the top, and at the bottom you can see the input-output paths. So we used 48 paths, but we didn't use them all. It's just that the probe card was 48 pins. So this is the measurement setup. So we had the chip connected to the probe card, and that was connected to the FPGA through some level shifters to adjust the supply voltages. And then we did some simple measurements, of course, with a fixed key, because we could only burn the key once. We used this key. We applied 1,000 plaintext automatically, and then we checked if the ciphertexts were correct. And we played around a bit with the supply voltage and with the bias voltage. And this gave us the correct results. The maximum clock frequency was also very low, so 10 kilohertz. We needed a number of cycles to shift in the plaintext and to shift out the ciphertext and to do the actual encryption. So in total, this led to a latency of almost 32 milliseconds, which is large compared to silicon chips. But like I said before, for those applications that are focused on low cost and this bendability, biocompatibility, and where performance is not important, this is a valid option. Okay, so we looked at digital crypto circuit, and we at least have some minimal version of that working. Then the next thing is key storage. So like I said, there's only this one-time programmable storage, either with a laser or with ink. We chose for the ink option. So this is a microscope image of part of the chip. So you can see on top bit 26 to bit 36, so 11 bits of the 80-bit key. And each, so these are actually the key bits. Huh? And they are each connected to both the ground rail and the power rail. And here you can see a piece of the digital logic. And like I said, before turning on the chip, you need to make sure that one of these wires is cut. So if we zoom into these 2 bits, then you can easily see under the microscope that this wire has been cut and this wire has been cut. So it's super easy to just read out the key, which is something we don't want, of course, because just by looking at it, you can even see it. So it's the same as putting a sticker on it with the key. So that doesn't make sense. Yeah, and so you can see, yeah, this one is still connected to the power rail, so this key bit is 1. This one is still connected to the ground rail, so this key bit is 0. So the problem is you can easily read out the key. The features are large, the chips are not packaged, so that all doesn't help. You don't even need to depackage to read out the key. So this is the method that we propose to at least make it a little bit harder to read out the key. And that is also based on lasering, but in a different way. So the effect that we will use is that if you can cause a temperature change by using a laser on the TFT, then this can shift the threshold voltage of the TFT. And this has to do with additional oxygen vacancies that will occur or will be generated through the laser, through this temperature change, and which then make or bring the transistor from a non-conductive state to a conductive state. So by applying the laser on the TFT, with the same input voltage, we switch the transistor from off to on. So what you can see here is the current through the transistor and the voltage applied at the gate. If we apply this negative voltage here to the transistor, then in normal mode, it would be off. If we now apply the lasering, then the transistor will switch on without changing anything to the input voltage and without cutting any wires. So with a fixed input voltage, the TFT switches from off to on. And this we can use in this way. So if we put a TFT here and a TFT here, and we connect the key bit to both the ground and the power supply, and we put this TFT in between on both sides, then before lasering, you get something like this. Both TFTs are not conducting. And of course, for each of them, we apply this negative voltage at the gate, and then the key bit is here. Yeah. So when you apply lasering to the left transistor or the bottom transistor, then that TFT starts conducting and key bit becomes 0. And if you do the same for the other TFT, then it becomes 1. And then we thought, okay, great. So this we will not see under the microscope because we're not cutting wires. And then we had a look. And then we were not happy because you could still see it, the difference. So on the left side, you can, yeah, maybe on this slide not, but in real life, we could. So on the left side, you see a laser TFT. So this is the top view of a TFT. On the left side, you see a laser TFT. And on the right side, you see a TFT that's not lasered. So you can easily see there is a visible difference between the two. So that's a problem because then, yeah, our problem is not solved yet because you can still read out the key. Maybe it's a bit more difficult and you have to look a bit more carefully, but still the difference is visible. So then what we thought of doing is apply different settings of the laser to cause different VT shifts that cannot be visually distinguished. So we applied a lot of settings of the laser to TFTs, and then you can see here everything that we tried, where, so this is this ID-VG graph that I showed before, where you have the current through the TFT on the y-axis and the voltage at the input of the TFT on the x-axis. And what you can see is before lasering, for all these settings, you see that the blue curve, for example, here, the blue one is the way that the TFT behaves before lasering, and then the red one is how it behaves after lasering. And then we found some good combinations, like, for example, this one. Like, if you apply these settings, and I will tell you which ones these are, to the TFT, then you can clearly see a VT shift here. And if you apply these settings, you can clearly see that there's almost no VT shift. So if we zoom into that, then we get something like this. So like I said, the input voltage stays the same. That's this negative voltage, for example, -5 volts. And with these settings, attenuation of 45 dB, low energy mode, 1 pulse applied, the shift of VT was significant, such that the transistor switched from off to on. And in the bottom image, the shift, so attenuation of 35 dB in low energy mode and 2 pulses applied, the shift in VT was not that significant, and the transistor was not switching from off to on. And at least by looking at the microscope images again, we could not see a difference. It could be that you could apply, I don't know, machine learning or so to still see the difference, but yeah, it's anyway better. We still just have to use the laser like we did before for cutting the wires. And visibly, there is no difference yet. So this turned out to be a good solution. Yeah, then we could also use ink here. Of course, like I said, the ink drop you could also see, yeah, if you just use that to program the key. But we're also thinking of using ink to cover everything, actually. So if the ink is non-conductive, because otherwise the chip would not work anymore. If the ink is non-transparent, to cover everything, and insoluble, such that an attacker cannot just solve the ink, then we could use that to actually prevent the readout of the key and also prevent IP theft. Because if you want to look at the circuit, you can also easily do that in this technology. Of course, the ink needs to be applied on both sides of the chip, because you can look from both sides to see the circuit, because it's plastic. Yeah? So, but this is something we are still looking into. If we look at key storage mechanisms in general, then we looked at this one-time programmable option now, which was additive with ink or modificative. That's actually what we did with a laser. I already said that non-volatile memory like flash we don't have in this technology. And yeah, battery-backed volatile memory, yeah, we also don't think it's very practical to use that on these chips. So these things are not possible yet, and the only thing we can do now is like our options that we just proposed. Of course, another thing that we could do for the key is to use a buff, and this has not been explored in this technology yet. So as many of you know, of course, the difference with traditional key storage mechanisms is that buffs do not store a key, but generate a key. And you can also not see the key, or you can never see the key, but if the power supply is off, then the key is also not there. So keys are generated when needed. Since this is also joined with the school, I will quickly explain very briefly what a puff is. Puffs use process variation for generating actually device unique values. And this can either be keys, or this can also be used for device authentication. So in this figure that I stole from here, you can see that when the same challenge is applied to two chips that actually have the same puff circuit, that these both chips will respond with a different response, which can then be used to authenticate the chip, or it can also be used as a key, which is then different or unique for each chip that holds the same puff circuit. And the fact that it's different is through process variation. So process variation is used for device uniqueness. And then if you use this for device authentication, then what is done before the puff is deployed, or the chip which holds the puff is deployed, then you need to enroll the puff through a database server that applies different challenges to the puff, records all the responses, and keeps all these challenge response pairs in a database. And then in the online phase, where the chip is really in the field, a server can send a challenge to the chip and check if the response that comes back is correct through this database server. So that's in a nutshell what happens. Now, if we want to look in our technology, we didn't try this yet, but just reasoning about how well this would work in our technology, then the properties that are important for puffs are easy evaluation. So it should be easy to like apply a challenge and then easily get a response back. I guess if we could put, if we could put puff circuits in our chips, then we could make that happen. Uniqueness, yeah, that's something to be checked, but there's also process variation in this technology, so we should be able to use that. Then this I will come back to later, reproducibility or reliability. So under different operating conditions, such as temperature, different supply voltage, the puff should always give the same response, at least after some post-processing. Then unclonability, you should not be able to clone the chip. Unpredictability should be a one-way function, and tamper evidence, if somebody tampers with the chip, you should be able to see that from the puff response. So all these things seem like they should work in this technology as well. It's only this thing that we don't know yet, because there's another factor here in the operating conditions, so to say. And that is that it's not only temperature and supply voltage that we need to check here, but also the degree to which the chips are bended or stretched, because that could also have an influence on the puff output. If you build a digital circuit, then you just want to make sure that the zeros and the ones that you expect to come out are there, and then you have like some margin, and it has already been shown that even under bending or stretching of these chips, the digital circuits still operate correctly. But if you build a puff, it's a bit more sensitive to all these things that you do with the chip. So the question is, will the puff still produce a reliable output when the chips are bended or stretched? And that's something to be checked. So that is the challenge there. So to come back to our hardware security requirements, we looked at very simple digital crypto circuits. We found a method to program the keys through this with lasering, and yeah, we were not able to visually distinguish between the 0 and the 1. Yeah, and I said something about puffs, which are also an option, but still need to be explored. Then the next thing is the generation of nonces. For that, what do we need? So a nonce is a number that is only used once. So either you need a true random number generator for this, or you need to keep track of which numbers you used before. Because if you use a pseudo random number generator, you power off the chip, you power it on again, you need to know which nonces you used before. You cannot start again from the same one every time, because then there is no freshness. Like I said before, there is no electrically readable, writable, non-volatile memory in the technology, so that we cannot use. So the only option, in our opinion, is to use two random number generators. And there, the challenges are actually, if you look at these pseudo CMOS gates, because we only have n-type logic, the transfer characteristic of an inverter looks like this, where for CMOS it looks like this. So we don't know if we will have like too much bias because of this. We need to check actually which TRNG circuits are valid when we use pseudo CMOS logic. If it still holds that you can get, for example, by using ring oscillators or something like that, you get the same randomness, or loops of inverters. No. Then to end like our case study, so actually our second chip is fabricated now, and there is a true random number generator on it, so I hope to be able to say more about that soon. Remaining challenges, if we want to be compliant to, for example, NFC standards with this flexible tag, then we need to stay within certain delays for the communication between the reader and the tag. And that is actually still a challenge, because we only looked at the crypto circuit at the moment, and there's of course some other things that need to happen, like the communication itself also takes some time. So we need to see if it can really be compliant with this. So research has shown that NFC compliant tags can be built, but without crypto or without security at the moment. So we need to check if it fits in. Of course, if we need mutual authentication, it causes an even longer delay. If we want to go to public key crypto, like there was like a lot of active research 15 to 20 years ago on public key crypto on RFID tags, and if we want to go that way, then yeah, that poses even larger challenges. But also it depends on how the technology evolves, of course, because the number of transistors that we can put on a chip, that's not research that we will do, but that's for technology researchers. Okay, so this is to conclude that case study on flexible electronics on plastics. But like I promised, I also wanted to get back to emerging technologies in general. And I already mentioned memristors, fully depleted silicon on insulator technology, so ultra-low leakage technology, and then other types of flexible electronics. So this is an overview that we made for a paper that will appear in a special session at the Design Automation Conference this year, back. So just to give you a quick overview of what has been done, or what in our opinion has been done. Maybe Maddie, you can already tick some more boxes, I don't know, then you can tell us. So for memristors, there has been a little bit of work on crypto circuits using memristors. There has been a little bit of work on true random number generators, and there has been a lot of work on puffs, actually. So both on the construction of puffs using memristors, but also on attacking puffs using memristors. Because, like you know, using machine learning, we can break almost any, I guess, strong puff at the moment, and this has also been applied to memristor puffs. Then fully depleted silicon on insulator technology. The technology that is mostly used is 28 nanometer FDSOI of ST microelectronics, actually in almost all these papers, I think. There have been some experiments on puffs and TRNGs in this technology. Then crypto circuits, like an AES circuit, has been built in that technology, and fault analysis. So some researchers experimented with fault analysis. And then there were also side channel attacks, power analysis attacks applied to these circuits. Then if we go to flexible electronics, then first we can look at printed electronics. So maybe I didn't make it clear before, but yeah, this is the technology that we use, the metal oxide TFT. So this is not printed electronics, but everything is deposited on the plastic. So there is a difference. This technology, electrolyte gated field effect transistors, that is printed electronics. So there the fabrication process is even simpler actually than the technology that we use, like you do it in-house, I guess, at the university even. Yeah, and most work is also done by Mehdi then. So there has been some work done on puffs in this technology, and also on true random number generators. And probably I'm missing some references, so I apologize. Then there's also other types of TFTs that are deposited on plastic substrates. For example, organic TFTs, and there has been one experiment on puffs in that technology. And then the last line is the case study that I showed. So there we looked at the very small crypto circuit, and also on, yeah, I called it obfuscation here, like making sure that you cannot see the key. Obfuscation is a broader term, of course, but I think it's also applicable. And then, yeah, this whole overview you can also see in our paper that will appear soon. So yeah, the message is actually, this is the last slide. The message is that there's a lot of holes here. So a lot of things that can still be done and that are also reasonable to be done or important to be done. And also, if you follow this international roadmap that I talked about on the first slide, it's not only these technologies, but there's a lot of emerging technologies. So it's worth to take a look at which ones are accessible already for research and what the holes still are to make products in those technologies secure. And with that, I conclude. Yeah. I was fast. No.
Is this on? Thank you very much, Nina, for this very interesting and insightful talk. Do we have questions? Yeah. Please, yeah, exactly. Please raise your hand. Awesome. Thanks.
So thank you for your talk. You mentioned two methods for programming the keys.
Yeah.
I maybe have a third one. Have you talked about eFuses?
But those are also technology dependent, I guess. Huh?
Okay.
So which specific technology for the fuse would you have in mind?
I don't have any.
Yeah, I see. Yeah, because indeed, that would be an option, but in this technology that has not been explored. So maybe it's something to look at, but it depends on if that's possible or not, because yeah, fuses typically use, like, you have to push like a large current through the fuse to or apply a large voltage, depending on if it's a fuse or an anti-fuse. And I don't know if that's already possible in this technology. And I also think that you would be able to see the difference then, but that's of course an open question. Yes. To which extent it would be visibly different between 0 and the 1 then actually, for the key. Yeah. Thanks. Yeah.
Thank you.
Thank you very much for this nice talk. My question is, you mentioned, I'm not quite sure, but you mentioned this technology is less reliable comparing with CMOS, correct?
Yes.
Could you please explain why? I didn't get the point.
Yeah. So one reason is the fact that we can only use N-type transistors, and we have to go to this pseudo CMOS logic that I showed. So CMOS logic, normal CMOS logic is very reliable because you always have like a conducting path between your supply voltage and your output through the pull-up network, or between your output and your ground voltage through the pull-down network. But in this case, if we only use N-type transistors, then we cannot have the same effect. So, and like I showed you also this transfer characteristic when I talked about true random number generators. So the noise margins, oh, sorry, wrong direction. Yeah, here. If you look at, for example, the transfer characteristic of this pseudo CMOS inverter compared to a CMOS inverter, then you can see that the noise margins are smaller actually. So here, noise margin means, like, for example, if your power supply is 5 volts, then down to maybe 4 volts or 3.5 volts, that's still a logical 1. And at the bottom you have 0 volts, maybe up to 1 volt or 1.5 volt, that's still seen as a logical 0. That's the noise margin that you have. For pseudo CMOS logic, this noise margin is much smaller, especially here at the top side. The inverter flips values much more easily. So you have a lot less margin there, which makes it more difficult to build reliable circuits. And besides that, in general, in this technology, it's more difficult to put a lot of transistors on the circuit yet. Sorry?
To get one more than 0.
The
bias here in this technology.
The margin is...
Yes.
Yeah.
The margin is more towards 1. You have the...
Yes. It is. Yes.
Yes.
Yeah.
Thank you very much.
So maybe for these technologies that we have, from one side the transistor limitation, which is for CMOS is cheap, maybe we, I don't know, maybe thinking loudly, that whether it makes sense to rethink this, let's say, cryptography and even locking, because the way that it is done for CMOS, again, because you can, from one side is the transistor is cheap, so it is not an issue that, you know, have an extra logic, and from the other side, because of the mass-based processing, you have to fabricate in large volume. So if you look into the different chips or cryptos that they have different keys, the layout looks the same. So it is basically the same chip, and then you program it afterwards. Does it make sense that, you know, to have some, let's say, like a bespoke crypto or bespoke locking, that, I mean, if you have 2 instances of the chip that have different locks, even their layout would be different. Yeah. So this way you have fewer transistors for that. I mean,
yeah, it might be an option, and also because the production process is cheaper here, you don't, I mean, you don't need to benefit that much from the high volume production because it's anyway different. So that could indeed be something to look at, yes. But that, yeah, that changes, of course, the whole mindset of how we design these algorithms. Yes. Thanks.
Hi, thank you for the nice talk. I don't really understand why the bias in the true random generator would be an issue, because I thought when you would use like a ring oscillator, you would associate it with like a randomness extractor that would unbias your fit. So, yeah, like as long as it's always the same bias, why would that be a problem?
Yeah, it could be indeed, but it's something to be checked. But it's a good remark. It might be that we just easily get rid of it. So it is something to check. But yeah, it's just that when we start building these TRNGs, we probably need to take into account that there is this effect, and then we need to check if it's there and how we can get around it. So yeah, thank you.
Interesting talk. What consideration has to be made if you want to merge this technology with the current CMOS one?
Yeah.
Except the power and...
It's a very good question, and actually I don't have a good answer to that, but I know that this company that is now commercializing the technology is looking a lot into hybrid solutions. So it is a subject of ongoing research, but I don't know enough to give the answer. So, but just to let you know that this is something that will probably happen because they do see the use case and they are looking at it. So, yeah, but it's a valid question, and it makes sense because the company is also looking at it, indeed. Yeah.
Other questions? Do we have any questions from the online audience? Not at the moment. I actually had one more question in the presentation. You already shortly hinted at it. So as there is not too much work done on it up to now, but do you foresee how difficult side channel attacks might be and fault attacks, these kinds of attacks? And are there potentially new ones? I don't know, maybe you can feel the temperature or of currents or something.
Good question. And I think before we look at that, we should first solve the other problems, because if you can just look at the chip, then and read out everything, then it doesn't make sense to do a side channel attack, of course. So also with regard to like probing attacks or so, the chip is not packaged, so everything is much easier. So before we really look into side channel attacks and fault attacks, we have to look at that, of course. And then, if you do a power analysis attack, I think it will be similar. Of course, the chips are larger, and the current that is drawn through the CFDs is larger. So probably the measurement setup needs to be modified to accommodate that. But for the rest, I assume, and of course, we need to take into account that we have these pseudo CMOS gates instead of CMOS gates, so the models will be different for sure than what we have now. But yeah, for the rest, I think the approach should be similar, taking into account all these modifications that we then need to make into to the approach that we apply.
Thank you for the interesting talk. So how you will take into account the environmental condition, because everything is on plastic. So how we will take care of the radiation effect, for example, let's say in terms of reliability, or maybe the temperature effect once it is fabricated.
If I understand your question correctly, then how will we take into account radiation, or
different environmental condition? It could be a temperature, it could be a radiation,
it
could be a moisture.
Like temperature and all these things? Okay, of course, that's something that has not been explored at all. So it's a very good question, and that's something that we indeed need to take into account and that we need to experiment with. So one question that now pops to my mind is how temperature resistant is the plastic substrate, for example. So those are all things that are actually partially also technology related, but then should be applied to our security research as well. So sorry, I cannot really give an answer, but thanks for the question.
So maybe one more question. Is there any prediction on scaling? Whether these...
So that's really the topic of ongoing research. So for example, one of the people I'm working with, Chris Mini, who was also co-author in our paper, he has an ERC grant that is really about that, so about scaling. And also, if you look at when we did this research in 2019, then we got up to 4,000 transistors, and that was then like the record. But now the new processor that they made, and that will be published at ISSCC, goes to 10,000 transistors already. So there is a lot of evolution there, and I also expect that it will continue like that. So we will be able to do a lot more in the future.
No, but we don't have a Moore's law for circuit.
I don't know if they have that actually. Yeah, probably there is something, I guess. But of course, it's a young technology also, so you cannot look backwards that much. Yeah.
Okay, maybe an opportunity for
yes,
another work.
Yeah. Okay.
Other questions? Otherwise, thank you very much, Nina.
Thank you for having me.
We also got you a little present with some marzipan.
Great.
So, probably good, yeah.
Thanks a lot. Thank you.
So thank you very much for coming.
Thanks.
Sorry, yes. And, so we now continue with a short break. There's a coffee break, so please enjoy a short break and some interactions. And yes, for the people participating online, we'll resume at 2:15, which is in about 15 minutes. See you in a moment.
So hello everyone. We will start with the first technical session now, so please have a seat if you don't have already. Okay, so in this session we have 3 great papers on public key cryptography. Our first paper is on pairing-based cryptography, and it will be presented by Arthur Lavis. Floor is yours.
And thanks to the program committee for accepting our paper. So Arthur Lavis, I'm a PhD student working for Mint Saint-Etienne and Thales. And today I will present our joint work with Alexandre Berzati, Nadia Helem Rabé, Jean-Baptiste Rego, and Julien Proy about hardware implementation of pairings at updated security level. So during this presentation, I will start by the context by explaining what is a pairing and why we're interested in such things. Then I will go through pairing arithmetic and just to explain what kind of function we had to implement. Afterward, I will present our hardware implementation of a generic coprocessor, and then explain how we implement pairings and what are our results. And I will conclude and discuss future research direction on the last part of this presentation. So first the context. So pairings are bilinear functions. They rely on elliptic curves and extension field arithmetic. And we're interested in such a function because of the bilinearity property, which allows the creation of interesting protocols such as the identity-based encryption proposed by Bonin-Franklin in 2001, or the self-knowledge non-interactive argument of knowledge proposed by Benson, also called as Zcash, which is currently used in the Zcash cryptocurrency. For implementing pairing at 128 bits of security, the curves proposed by Barreto and Nairing, also called BN curves, used to be the most efficient. So the majority of Piero's work focus on implementation or arithmetical optimization on these curves. But in 2016, Kim and Barbulescu present an attack on pairing, and the BN curve with a 254 bits modulo, which used to provide 180 bits of security, now only provide less than 100 bits of security. So now to ensure pairing security, we have either to increase the key size or to switch to other curves, such as the one proposed by Barreto, Lin, and Scott in 2002. If we want to increase the key size before the Kim and Barbulescu attack, the BN curves implement a pairing on BN curves required to compute almost around 12,000 modular multiplication on a 254-bit modulus, and now you have to compute more than 70,000 modular multiplication on a 462-bit modulus. So the BN curve is the most impacted by this attack. And other curves like BLS12 are a bit less impacting, since there are only the keys that increase, and the BLS24 is not impacted at all by this attack. So after this work, Barbulescu and all make an intensive literature inspection in 2018, and they try to find out as many pairing-friendly curves as possible. And to estimate the complexity of pairing on this new curve, they count the number of modular multiplication, denoted MP, and they try to estimate the complexity of one modular multiplication by the square of the number of 64-bit integer required to represent P, which should correspond to the complexity of a software implementation on the 64-bit CPU. They find out that the BLS curves with a number degree of 24 is supposed to be the most efficient one and 128 bits of security. Afterwards, the curve BLS12 is also supposed to be interesting at this security level. Another approach from Georvik and all is to find new curves especially resistant to Keyman-Barbulas attack. And they provide one curve with a number degree of 8, which is supposed to be just a bit less efficient than the LS12. Afterwards, there are plenty of other curves with a similar complexity level, but we decided to implement the 3 best pairing available on the literature. On these 2 curves, the most efficient pairing is the A pairing, which consists in 2 distinct steps, which I will detail in the rest of this presentation. So for the first step, it consists of computing the Miller algorithm. I don't have the time to go through detail, but we follow Costello and R recommendation, and we use mixed affine projective coordinate to compute pairing on BLS24 and BLS12, and we use mixed affine weight 1-2 coordinate to compute pairing on GMT8 curves. So to compute the Miller algorithm, you have several functions like square and sparse multiplication in the extension field, but what is important here is that every operation can be implemented as a succession of modular operations. The second part of pairing computation is, so for an example, if you want to compute the multiplication in FP2, you can see an element scene are a polynomial of degree 1 with coefficient in FP, which means modulo P. So one of the methods to compute it is to use the Katsuba method, which requires 3 modular multiplication in red, 5 modular addition in blue, and 1 multiplication by a small constant alpha, where alpha is equal to 5 for the GMT8 curves and -1 for BLS12 and BLS24. So for the second part of the pairing computation, it consists to raise the result of the Miller algorithm to a big exponentiation. So we follow Georvik and all decomposition, where the final exponentiation is split into an easier part, p up to 4 - 1, and an hard part involved. During the hard part of pairing computation, we are in what you call in a cyclotomic subgroup. So there are fast arithmetic in this subgroup. For example, an inversion in this subgroup costs only a few modular addition, and there are also more efficient scoring. The formulae proposed by Granger and al. Only require 2 scoring instead of 3 required by the Katsuba method, for example. But the drawback of this method is that it requires 1 inversion by u, which is neglectable when u is equal to -1 or is the power of 2. But in the case of the GMT8, this division by u can be seen as a multiplication by uv divided by 4. So it costs at least 4 modular multiplication to compute this inversion. So we provide a new cyclotomic scoring formulae, which only require two scoring as the previous formulae, but which doesn't require any division by u. So this formula is most efficient to compute a pairing on the GMT8 curves. To compute the final exponentiation on the BLS24 and BLS12 curve, there are similar operations to compute with also fast arithmetic in another cyclotomic subgroup. But once again, what is important is all this operation can be implemented as a succession of modular operations. So to build our hardware design, we want to be able to implement several pairings, and modular operations are the only common point between all these curves. Moreover, the modulo must be configurable since it's not the same from one curve to another. We also aim at providing a lightweight coprocessor which could be suitable for both ASIC and FPGA purposes. So in this way, we base our memory model on a single port RAM, and we try to find a compromise between computation time and area. We also wanted to reduce the penalty brought by additional operations, which are neglecting from the estimation from Bode and all. But there are almost 4 times more additional operations in pairing computation than modular multiplication. To do so, we want to compute these additional operations in parallel with the modular multiplication. Finally, we choose to use a 64-bit architecture in order to reduce the number of required memory accesses, which also allow a faster addition. So, to compute the modular multiplication, we use the hardware architecture present here, which is a variant of the one presented by Wang and al. And it's based on the algorithm multiple radix 2 Montgomery multiplication, where the multiplication is calculated with a succession of addition, and where each process, small unit or processing element compute the multiplication with only one word of the modulo. Finally, with this architecture, we are able to compute one modular multiplication in around log 2 of P clock cycle. An interesting fact is that with this architecture, there are no memory calls during the majority of the computation, so we can compute additional operations in parallel. For other operations, we use this component, which also stores the modulo in a register to reduce the number of memory accesses. And then we use 2 64-bit adder subtractor, one to compute the addition and the other one to compute the reduction. We also add a small component to be able to compute the division by 2. And with these 2 components, the cost of the modular multiplication is 60 times higher than the one of a modular addition. But since there are 4 times more additional operations than modular multiplication, the cost of additional operation cannot be neglected. To implement pairing, we did our development and test on the AMD Xilinx Kintex 7 FPGA, and we package our multiplier with our adder together with one scheduler and one instruction decoder into custom IP. In this way, we are able to launch a modular operation with a single 32-bit instruction. Then the high-level unit is just used to schedule the modular operation. So for prototyping purposes, we choose to use a micro-blast CPU from Xilinx because it was easier this way. But we also can replace this processor. Finally, we use a UART communication port to allow external communication with a computer, for example. So with our architecture, without any parallelization, the additional operation represents around 25% of the overall calculation. But since we are able to launch it during multiplication, we can parallelize some of them. For example, if we go back to our example with multiplication in FP2, we are able to save, to compute in parallel the operation in gray. So we can save 4 modular addition and the multiplication by the small constant alpha. By doing this with the multiplication scoring in FP2 and in FP4, we are able to cut computation time by around 50%. To ensure the correctness of our design, we build the following test sequence. We use Magma calculator software to generate the points P and Q, and then we use a Python script to compute a random element alpha. Then we compute on the computer alpha P and alpha Q and send this value to the FPGA. The FPGA will compute the pairing of P and alpha Q and the pairing of alpha P and Q, and send back this result to the computer. Since pairings are supposed to be bilinear, if these 2 pairings are equal, we check the bilinearity property of our implementation, and which allows to ensure the correctness of our implementation. For our result, the comparison with previous work is difficult because lots of it worked on BNCore, and there is no hardware implementation of pairings at updated secure level on new core. So I decided during this presentation to only present our result. what we can see is that the time area product of the three curves is quite similar. Just the GMT8 curve is 5% better than the two other. But what is interesting here is that the best curve will depend on the most important metrics. For example, the curve BLS24 occurs less area because the modulo is smaller than for the 201, but the memory required to implement pairing is much smaller on the GMT8 curve than from the two other. Finally, if you want to have a faster pairing implementation at 100 TB of security, with our architecture, it's better to choose the GMT8 curves. It seems that the GMT8 curve is more suitable for pairing implementation on lightweight devices than the two other curves. To conclude, to our knowledge, we provide the first hardware implementation of pairings at updated security levels. And we design a generic hardware coprocessor suitable for compute pairings on various cores, which enable parallel computation and with an interesting compromise between computation time and dedicated area. We use a micro-based CPU for prototyping purposes, but since its only task is to schedule modular operation, this CPU can be easily shown with a RISC-V CPU or with a dedicated FSM. And finally, we also provide a cyclotomic scoring formula, which is more convenient to compute the final exponentiation for the GMT8 curves. I didn't have time to present it today, but we also provide in paper one implementation of pairings at 192 bits of security on the BLS24 curves, and we are able to compute it within 184 milliseconds, which make pairings at high-level security affordable for lightweight purposes if you have enough memory, of course. As a future research direction, we could look at what we could implement the SIG post-quantum protocol with our architecture, because this post-quantum protocol also relies on elliptic curves and extension field arithmetic. So our coprocessor should be able to have interesting performance for this protocol too. These are the references I used during this presentation, and if you have any question, I will be happy to answer it.
Thank you for the nice presentation. Are there any questions from the audience? Not. Then I have a question. So your design, so did you synthesize your design for each different parameter set separately?
Yes, because if you look at, as I said, the modulo is smaller on the BLS24 curve, so you don't have to have all the components, but if you synthesize the component for the GMT8 curves, it should also be able to compute the BLS24 pairings since the modulo is configurable.
Okay, so at least you have a degree of flexibleness so that you can change between the curves. Okay. Yeah. And maybe another question, you said it's very difficult to compare what the overhead is now between your work and the work needed to implement the previous parameter sets that were previously thought to be 128 bits. Can you maybe give a very rough estimate? Is it 20%?
Yeah, I can add it. Sorry. I didn't implement the BAL29 curves, but I also implemented the BLS12 curves at the previous security level. And if we compute full-time RSO, it's around 36,000 milliseconds time slice, which is better than the two previous ones from Wang and from Salman. The work from Jan, which uses RNS computation, bring a better time error performances. But we didn't count the DSP, and they use triple port RAM, which allow more parallelization. So I think for Tamara productivity also interesting compared to previous work.
Yeah, sure. The hardware implementation is very difficult to compare. And then are there already next? So if there's even more cryptanalysis and we find that this 128-bit doesn't hold, are there even more curves after that?
Yeah, so here we can also provide new clones which prime on the DW, which are supposed to be less impacted by attack like Clement Barbarescu. But today the computation framework of the score are 2 or 3 times harder than on the Cry implement in this paper.
Thank you. Any more questions from the audience or online? If not, then let's thank the speaker again. And we move on to our next talk, which will be given by Gregor Land. And he will talk about a hard crystal. Okay, the floor is yours.
Yeah, thanks for the introduction. Also, thanks for the opportunity to talk at this conference. What already said, my name is Georg Land, and this is joint work with Pascal Sastrich and Tim Gunesu. And apparently, as the title says, we implemented a thing called dilithium. So let's first of all clear up what is dilithium. It is a lattice-based post-quantum signature scheme. Post-quantum here refers to that it can withstand attacks, or as we know of today, it can also withstand attacks that are launched with a sufficiently big quantum computer. And as many of you may know, there's currently the NIST standardization of post-quantum crypto going on. And there, in the currently maybe final round, dilithium is one of the 3 finalists. And in this standardization, several aspects are evaluated. For example, like cryptanalytic aspects, but also like how efficient can we, or how efficiently can we implement this? And yeah, let's have a look at what exists already for efficient implementation. So we have software implementations; those are already quite fast available, quickly available for ARM Cortex-M3 and M4. Then 2 years ago, there was a high-level synthesis FPGA implementation for the RTX-7 family of FPGAs. And then in parallel to our work, there's been also an FPGA implementation for the high-end Vertex-7 family. But both of these implementations have some drawbacks. So first of all, they do something that very often is not realistic. So, for example, they have one single core for key generation, and this might be okay for many scenarios. But usually, or for many more scenarios, you'd like to have like a full service core that can do key generation, signing, and verification. And the second drawback, and the even more important drawback, is that they only implement around 2 parameter set. So starting, I think 1 year ago, there was the 3rd round of the NIST, not a competition, and for dilithium, the parameter sets and some details changed quite a bit. So both of these implementations lack a bit of relevance for the 3rd round. So what did we do? We present the first implementation of the dilithium that really targets the RTX-7 platform, save the high-level synthesis implementation. And as we'd expect, we will see this later in the comparison, the high-level synthesis implementation is rather big and slow. Then secondly, our implementation is also the first to implement the around 3 parameter sets on FPGAs. And our implementation is also the first one for dilithium that really supports all operations. So meaning our cores usually can do, or they can perform key generation, signing, and verification, and also something that is left out very often, some auxiliary operations like computing the message digest, or packing and unpacking the keys. So we have the keys internally as polynomials, or polynomial vectors, but when they are transferred via network, then usually they have some kind of data layout. They are packed, and we need to unpack them to transfer them into our internal representation. And for better comparability, actually, we also did a single operation course, so a core that or several cores that only support key generation and the respective auxiliary operations. Okay, then I'd like to introduce you very briefly and leaving out many details to what happens in dilithium. So for the key generation, we sample the values A, S1, and S2, and from these we compute the value T. And in the end, you see A and T is the public key, and S1 and S2 is the secret key. What are these values? A is a matrix of polynomials, and T, S1, and S2 are vectors of polynomials. Then A is a uniformly random modulo Q, so every coefficient in every polynomial in this matrix is just uniformly random modulo the prime Q, which is a system parameter. And then S1 and S2 are also uniformly random, which is quite nice, so you don't have like Gaussian distributions and so on. So it's also uniformly random, but with a smaller bound. So for example, from -2 to +2, or from -5 to +5. And then an important implementation detail is that we can speed up the multiplication with the entity number theoretic transform, which is kind of a FFT performing on polynomials, and then we can just do pointwise multiplication of the coefficients to in the end have the product of two polynomials. So on the right side you can see our let's say high-level architecture, and I will explain how we map this to our how we map the functionality to our modules. So you can see there is the sampler module. It's actually like 3 modules. And that uses Ketchak. So Ketchak is always used as in the shake configuration to have a pseudo-random stream of bits, and from this pseudo-random stream of bits, we sample like the values A, S1, and S2. And then we have the matrix vector multiplication module, which is kind of a master for entity module and the multiply accumulate module to perform this matrix vector multiplication and addition to compute the value T. So moving on with signature procedure, signing procedure. Again, on the right side, you can see how we map this in our architecture. So first we sample a polynomial vector Y, so it's a vector of polynomials. And again, it's a uniform distribution, but this time it's really broad. So for example, something like -2 to the 18 to 2 to the 18 to +2 to the 18, but still uniform. Then we multiply A with this sampled polynomial vector Y, and then from the resulting polynomial vector, each coefficient is rounded. So it's Hybrid's operation is a rounding operation, and it's not just shifting, it's really more like a rounding operation. And as a result, we have the value W1. And we concatenate this value W1 with our message and absorb this to shake using the Ketchak module. And from the output stream of shake, we feed a deterministic procedure called sample and ball, which returns a single polynomial, which is fixed weight. So it has a fixed number of -1s and +1s, and all the other coefficients are 0. Then we compute the signature candidate Z, which is like adding this broad noise of Y to our small secret key. Yeah. So this can be done without the matrix vector multiplication module, only with the entity and MAC modules. Yeah, but then, and this is something important about dilithium, so we check whether Z leaks information about the secret key. We do this with the help of the value S2 also, yeah, so that's where S2 is used actually. And if so, we need to start over, yeah, and we need to repeat until we have found a valid signature candidate. Yeah? And if finally we have found a valid Z, then we return Z and Z as our signature. Verification now is quite simple. We try to reconstruct the value W1, but now without knowing why, and we can do this by multiplying A times Z minus C times T, A and T from the public key and Z and C from the signature. And if the signature is actually valid, then this will result in the same value W1, and yeah, then obviously this will be also the same, yeah, so with the input of the message. So this check will also hold if it is a valid signature, and also we need to check if Z is sufficiently small, so else there would be some cryptanalytic attacks. Yeah. So far about the high-level architecture. I want to go into further details about the entity, because usually for these lattice-based schemes that enable using the entity, this is like the centerpiece of any arithmetic, yeah, and speeding up the entity will speed up basically any arithmetic. And what we did is we took a quite recent implementation from Chess 2020, where they had the entity implemented for New Hope. And the basic characteristics of these implementations are that there are two layers merged, which results in a double throughput. Obviously, you also then need two butterfly units. Yeah, butterfly units are really the centerpiece of the entity. Then again, and also this poses the memory requirement of reading and writing 4 coefficients simultaneously. So reading 4 coefficients and at the same time writing 4 coefficients of a polynomial that is transformed. Yeah? So let's see how they did it. Yeah? And this is a pretty common approach to implement the butterfly unit. It is, so you can see the multiplication there in the figure in the bottom middle. And the usual approach is for multiplication, we use DSPs because it's nice and fast. Yeah? And all the other arithmetic marked with red in the figure are done with lookup tables. Yeah? So here you can see our butterfly unit, which does algorithmically the same, or nearly the same, yeah. But we leverage really all the functionalities of DSPs. Yeah? So in the bottom two DSPs, 1 and 2, we would need to use them for the multiplication anyways, but the Xilinx DSPs, or for the DSPs for the RTX7 family, also allow, they also have a pre-adder stage, and they also have a full ALU stage after the multiplier. Yeah? And usually this is just not used, yeah? But we thought it would be nice to have any arithmetic in DSPs. Yeah? And then for performing the forward and the inverse transform with the same butterfly units, we even reconfigure the DSPs at runtime. Yeah? So it's not reflashing the bit stream, it's really, you can reconfigure what the DSP actually does at the runtime. Yeah? And of course, there's a downside. Yeah? At least in our design, we have quite a few of delay stages, which causes quite a bit of usage of flip-flops. Yeah? And one difference you can see, there's also the input A minus B, but there we can use one DSP in SIMD mode to compute this value for both butterfly units. And another drawback is, of course, this is not something you can then just port to like Intel FPGAs, yeah, because they have completely different DSPs. So now with this implementation, you are really bound to Arctic 7. You know? Yeah, and the good thing is then, as we have put any of the arithmetic in DSPs, this gets really small, and DSPs are fast, so we have a small and fast entity. Yeah? And that's quite a nice result, I think. And for the comparison, for time reasons, yeah, just have a look at the paper. Then the second thing that's hard about implementing dilithium in FPGAs is the memory layout. So as I already said, the NTT requires that we are able to read and write 4 coefficients simultaneously. And we solve this by spreading one polynomial over 4 separate VRAM blocks. You know? And yeah, there we need to take special care such that the NTT is still possible there. So it's not just putting some coefficients there and some there. So you need to deliberately yeah, put them on the single VRAMs. Yeah, and this brings us to a theoretic problem, yeah, because then if we have 4 18K VRAMs for one polynomial, so then for dilithium 2, which is the smallest parameter set, we would need storage for 53 polynomials, and this results in like 212 VRAMs, so which is a high amount. Yeah? But we could tackle this problem. Actually, in 4 18K VRAMs, we can store up to 8 polynomials, but the polynomials, of course, have like dependencies. Yeah? So we cannot just put any polynomial next to each other because for some operations, we need to access multiple polynomials at the same time. Yeah? The best example is the matrix vector multiplication. So you can see the matrix with the blue color indicates that it's already in NTT domain. And the input vector on top is not in NTT domain. And what we do there is, first, in the first step, we perform the NTT on the first input vector polynomial. Then we have this also in NTT domain. And then we go on and perform the NTT on the second input vector polynomial. And at the same time, we sequentially read the first column of the matrix polynomials, multiply them with the now transformed first input vector polynomial, and write this to the result vector. Then we need to update in the next step. Yeah. So after this is done, then we need to update the result vector. So we need to read the result vector and write it at the same time while reading the column of the matrix and reading also the polynomial from the input vector. Yeah? And you can see there are many dependencies. But the good news is with some nice Python script, we were able to identify efficient memory mappings for all parameter sets. Yeah? So yeah, that's then the last step. After this step, in the matrix vector multiplication is finished. Yeah? So some comparison. As I already said, we have a full core, and we also have the keygen only core. And you can see this in the difference of the area usage and also of the frequency. Yeah? And you can see we have quite competitive results there. Yeah? So this is Arctic 7, which is a low-cost platform, and this is the design that has been published in parallel to our work for Vertex 7 high-end. And you can see we are way smaller, but also kind of slightly slower. Yeah? Which is always the trade-off for hardware. Yeah? And as I already said, as you would expect, the high-level synthesis is like off the table. Yeah, but that's a topic for that. Yeah? Then for signing and verification, again, there are the full cores. So you see there's always the same numbers for the full core because it's the full core that can do everything. Yeah? And single operation cores, again marked red now. again, also the high-level syntheses are off the table, yeah, both from the speed and from the area. And here, that's something to improve actually for our implementation. So this is the Vertex 7 implementation. You see they are quite fast for signing and not so big. Yeah, so they are 10 times faster, but not 10 times bigger than we are. Yeah? So there's some room for improvements actually. Yeah, and actually a competitor, like not a competitor, but Sphinx is also an alternate candidate. You can see that in hardware it is also quite yeah, let's say so, and it has also yeah, a big flip-flop requirement. But I'm just wanting to highlight that for the Vertex 7, yeah, their verification is not so fast, so we even can reach this nearly, yeah, while being very, very smaller. Yeah. So finally, some conclusion. What did we do? Yeah, we optimized the state-of-the-art NTT design. Then we implemented yeah, multiple cores, full service cores, single operation cores for the round 3 parameter set of the lithium. We targeted the low-cost RTX7 platform, yeah? And that is important because the lithium is one of the 2 promising signature finalists. It's promising because the 3rd finalist had some yeah, cryptanalytic attacks and is considered usually to be out of the race. Yeah, I'm not being sure about this, but it is usually people are considering this. Yeah, and yeah, we have the first implementation of round 3 parameter sets, and RTX7 it has an impact because RTX7 is chosen by NIST as the reference platform for these PQC implementations. Yeah. So finally, what remains open is at some point, actually, in our implementation, we chose the more straightforward way. Yeah, so so I'm very confident that very soon, or I think in the last days, there has been on ePrint even another implementation come up. So that will explore more parallelism. Yeah, so some of our submodules are really have some idle cycles. Yeah. Then what would be also nice would be one core that supports all the parameter sets, not only all the operations, but also all parameter sets. And finally, what's really open for the whole field, yeah, is to do research on the power and EM side channel countermeasures of these PQC schemes in FPGAs. Yeah? And with that, I close. Thank you for listening, and I'm happy to take any questions.
Thank you for the nice presentation. Are there any questions from the audience?
Hi, thanks for the talk. I was wondering, have you tried to use 4 butterflies instead of 2?
Yeah, you can try, yeah, but I mean, when using 4, yeah, then you need to read 8 coefficients simultaneously and write them, yeah. I mean, there's also some other works that have some special structures. They are not using 4; they are more like using a structure of 2 times 2, and then pipelining this through this. But I didn't try out. Yeah, so we really focused on using this very particular design and then transforming it to use leverage all the DSP usage. Yeah, so yeah.
And like in your implementation now, is the critical path on the butterflies or somewhere else?
It really depends, yeah. So some of the designs really are very big, yeah, because in the end there are multiple state machines, yeah, and switching between the state machines because there are multiple functionalities that use then the arithmetic, and it really depends on the core. Yeah, so there are many cores that we implemented, yeah, and yeah, really depends on the core.
Thank you very much.
Welcome.
Any more questions? If not, then I have one.
Yeah.
I'm always interested in side channel tech. So your work is, of course, doesn't feature any dedicated countermeasures, but is it constant time or it is, let's say, secret independent time?
Yeah, it is secret independent, yeah, time. So I mean, yeah, there's really no reason to have this in hardware. I mean, I think you would need to deliberately do this, yeah, to have it dependent on the secret. Yeah,
yeah, for the round trip parameters, that's probably,
yeah.
Previous,
yeah, maybe not. Yeah.
Previously had some rejection.
Yeah. Yeah, on the Y vector. Yeah, that was fixed. Yeah.
You also make quite hefty use of the FPGA dedicated features like DSPs, programs. So is your design then in any way, can it be adapted, the basic architecture for, let's say, ASIC or for other FPGAs, or is it really dedicated to this specific FPGA?
It is really dedicated to the RTX7 family. Yeah, I mean, the goal was really to say, okay, NIST has chosen this as a reference platform, and then let's see what can we get as a baseline. Yeah, so and then let's see, how many arithmetic we can put into the DSPs and save some LUT arithmetic and so on. Yeah, that was really the idea.
Okay, and maybe you can comment on if you use these programs and DSPs. How is like the utilization in the percentage? Is it like, do you maybe know that if you like use now, I don't know, 50% of the DSPs and 20% of the LUT?
Not from my mind. Very sorry. Very sorry.
Okay. There is more question from the audience.
But there's more than one RTX7, right? RTX7 comes in different sizes.
Yes.
So which is it? Is there a specific one selected by NIST? Or?
Yes. No. They just said it's RTX7. Yeah. You just use any RTX7. Yeah. Yeah. So yes, there's a range, and actually, what I can say is that on the very small RTX7, most of our cores don't fit. Yeah. And this is, I think, I mean, there are very, very small RTX7 FPGAs that don't even have enough lookup tables also. Yeah. So I think what I chose as really to implement it was some mid-range RTX7. Yeah? So there's also a range within the families. Yeah. But yeah. Anyways, the DSPs are really compatible. I mean, there's the same the whole family. Yeah. So you could port it within RTX7, definitely, and I'm not even sure, maybe even to Kintex 7. Not too sure about this.
The 7 series, they're all very similar.
Very similar, but the Vertex 7 recently and the UltraScale Plus, they have another DSP slice. They have DSP 48E2 instead of E1. Could be that they are downwards compatible, but they definitely have a bigger pre-adder stage, which would also help, actually. Yeah. Yeah.
Okay, thank you.
Welcome.
Questions online? No? Okay, if there are no more questions from the audience, then let's thank Georg again. And so for the third talk, we stay in the realm of post-quantum crypto. We even stay in the same algorithm family, kind of, in the crystal suite. And because now Hauke Malte Steffen will present his findings on side-channel countermeasures for Kyber, for the key encapsulation mechanism on the ARM Cortex M4. Stage is yours.
Okay, thank you. Hello, my name is Hauke Malte Steffen. I'm a student at TÜV IT, a master student, and today I'm presenting our work about the in-depth analysis of side-channel countermeasures for Crystal's Kyber message encoding, which we did on an ARM Cortex M4. So in the presence of quantum computers, public key cryptography we use today will be broken, and therefore we need post-quantum cryptography. And the aim of our work was to reduce the side-channel leakage of such a post-quantum cryptography algorithm. And therefore we will have a look first on background on the scheme we analyzed with this Kyber, which has to be implemented in a side-channel secure fashion. And then we will actually have a look on our side-channel analysis. We start with a reference implementation, then we apply a first approach which was aimed to reduce the leakage that occurs, and then we come to our main work where we developed 4 different countermeasures where we increase the degree of the countermeasures aiming to reduce the leakage. And finally, I will conclude our results. So let's have a look on how a Kyber key exchange could look like. In general, Kyber is a lattice-based key encapsulation mechanism that is used by, for example, 2 parties to generate a shared key to establish a secure communication channel. So we first generate a public and secret key pair as usual, and then the initiator on the right side runs the encapsulation procedure based on this public key and produces a ciphertext C and a shared key K. And then the ciphertext will be sent over the channel to the responder on the left side, who then runs the decapsulation based on the secret key and also produces the shared key. And then the shared key can be used for symmetric key material, for example. And if we have a detailed look into the encapsulation procedure now below, we see that the first thing we do is we choose a random message M of size 256-bit. And then we hash this message in line 2, and in line 3 we hash this message M together with a public key into a pre-key K bar. In line 4 we basically encrypt this message using the lattice-based encryption of Kyber. And in line 5 we finally derive the shared key by the pre-key K bar and the hash of the ciphertext. And if we have a look on this encapsulation sometime, we clearly see that it only depends on the random message and the public key. And the random message is the only variable inside here, which is unknown and randomly chosen. And with knowledge about this message, one could easily reconstruct the whole encapsulation. So if an adversary is able to extract the message M at any point here, she would be able to generate the shared key by herself. And now we have a look into the encryption function, but not too much into detail. So as underlined on the right side, we have there a decode function, which only based on the message itself. And this decode function is mainly called message encoding. And this is the function we actually having a detailed look on now. So this is a message encoding, the reference implementation that was submitted to the NIST. And what we actually do is we encode a single bit of the message to one 16-bit coefficient of a polynomial that will be used for the lattice-based encryption later. So what we actually do is, if the message bit is 1, we encode this message to a constant, a 16-bit constant, here denoted as C, and if the message bit is 0, we just set the coefficient to 16-bit 0. And this is done for all message bits. But how do we actually set the coefficients to their value? We first evaluate a mask, which is either 16-bit 0 or 16-bit 1s. And as you can see, we have and then this mask is binary. And then the coefficient is set by a binary AND operation between this mask and the constant we will set the coefficient to or not. And as you can see, these two possible states of the mask have a maximum Hamming distance of 16. And this could be a suitable target for a sidechain analysis. And now let's have a look what could happen if we actually implement this message encoding like it's shown here. So we measure the power consumption for one single trace. And here's the power trace for one execution of 1 byte, where we divided the single bit executions by vertical lines. And if there was process 0, you see a red circle, and if there was process 1, you see a blue circle. And as you can clearly see, we can clearly distinguish which bit we actually process there. And we can just read out the bits from a single power trace. So therefore, we applied the first approach by Emmett et al., which was aimed to reduce the leakage by reducing the Hamming distance of the two states of the mask from 16 to 1 by replacing this binary AND operation by a multiplication between the constant and just the message bit on the right side. And therefore we have only 0 or 1 now for the mask. But what we could show is that, again, for a single trace of power consumption, we can again clearly distinguish which bit there was processed, and you can again just read out what data was processed there and should remain secret generally. So then we applied an SPA for better conversion for the following schemes. So for these two implementations, it's obvious 100% of correctly classifying each bit of the message, but now we will have a look on the implementations and the approach we developed, and will then fill up this table. So our first idea was to make the operations to set those coefficients independent of the data we actually process, and therefore we define a second polynomial, a dummy, which will be then discarded after the message encoding. And then we first initialize both all coefficients of both polynomials with a constant, and if the message bit is 0, we do with it similar to the previous approach. We just set the coefficient to 0, but in contrast to the previous implementations, here we do not any additional operations like multiplication or binary AND operation. We just set this coefficient to 0 here. And if the message bit is 1, you see the coefficient is already correctly encoded. And then we can do the very same operation of just setting the coefficient to 0, but now operating on the other polynomial. Okay. And so now in Word we have to decide to which polynomial we actually write a 0 to. And let's have a look on the results. First, again, on the left side, a single power trace, where we now see some differences, but not obvious differences that really depend on the data we processed. So for example, on the left side, we have different data, as you see by different colors, but we have similar behavior. And on the right side of the left column figure, we have same data that was processed, but we have a different behavior. And then we build mean traces for a set of 8,000 traces for each group, build histograms for the point where they differ the most, and then we approximated these histograms with a Gaussian distribution, and these distributions are those you see on the right figure. And as you can see, they're overlaying very much, but they are showing a slightly different behavior still. And our SPA result shows us that this is the first implementation that drops the success rate here to 68.6%. And of course, to extract the whole message, it would be taken, you have to take this probability to the power of 256, since this is the size of the message. Yes, but as you see, we are not close enough to random guessing, okay? And therefore we stepped further and applied another approach, but additional to this countermeasure. So you see on the left side now, with another visualization of the previous approach of the dummy, and now we extend this approach by using not a single bit for the lookup, but more balancing it by using the full byte, and therefore we extend this list from size 2 on the left side to size 256 on the right side. But as you see in the results of the SPA, it does only slightly reduce the leakage, so less than 1% in this case, and therefore we decided to more hide to which polynomial we actually write a 0 to, so which polynomial we actually address. And then therefore we decide to randomly invert the order of whether we start with a polynomial P or with a dummy. So whether it looks like this or this. So we change randomly between these two possible states. And what you can see in the result of the SPA is that it reduces the leakage more than the previous approach, but again, we are not close enough to random guessing, so we are still at 64% for correctly testifying a single bit by the SPA. And therefore, we apply one final approach where we decide to randomly randomize the order of the bits and bytes we encode. And again, this is an extension of the previous approach. So we have below, we have the two polynomials, the original and the dummy, and let's assume that we have that the first message byte 0 is defined as above. And then we derive a randomization variable from it by XORing a constant value to it, which has a balanced Hamming rate. based on a previous implementation of the balancing countermeasure. And this fetching of this randomization variable could be a new target for an adversary, but in contrast to the previous implementations, we now do not processing the method bitwise, just using the full byte here. And then we use the last 5 bits of this randomization variable as byte mask to randomize the order of the bytes, and the first 3 bits used as bit mask to randomize the order of the bits of each byte. And how does it actually work? So we, instead of starting with byte 0, we add to our byte counter, we XOR our byte mask. So instead of starting with byte 0, we start with byte 0 XOR our byte mask, which is 25 in this case, and therefore we do not need byte 0 at this point in time. And we do the similar for the bits. So instead of starting with bit 0, we start now with bit 0 XOR our bit mask, which is 2. So we start at bit 2, then bit 3, and then bit 0, and so on. But again, this is an extension of the previous approach, and we do the very same procedure as before. So we work on the different polynomials based on the message bits, but now in a different and randomly chosen order. And on the left side now you see again our results for the 2 distributions, and now they are near equal. And on the right side you see the result of the t-test we applied for a set of 8,000 traces, and as you see the t-value now here remains below the threshold for the amount of 8,000 traces. And then we extended the set to see if this increases, and yes, it does for a set of 80,000 traces, so increase the set of traces by the 10 times of the amount compared to the previous implementations, but it remains only slightly over the threshold for this amount of traces, and it does only affect the trace sets for the template building for the FBA. So let's compare this final implementation to the previous results, and we see that by reducing the leakage, as we have seen in t-test 2, also the success rate of the FBA drops to 50.1% now. And if you consider the overhead on the rightmost column, please interpret this as an upper bound, since we did not focus on the overhead during our implementation. Now this success rate corresponds to random guessing. So let's come to a conclusion. We have shown that achieving resistance against such analysis is crucial for post-quantum cryptography implementations. And also for the first 2 XMR implementations, we could just read out the process bits from the power trace, as you see below, again in the table. And therefore, it would not improve the side channel resistance if we would process the message in shares, since we could easily read out all shares individually from the power trace for these 2 implementations. And therefore, at minimum, the dummy polynomial should be used to hide what operation we're actually doing, and it would be beneficial to introduce our randomization countermeasure even on top of mask implementations to ensure that even the bits of the mask of the shares cannot be extracted by an adversary. And for the whole presentation, we only had a look on the encapsulation side, and there the message is only processed once, and we only have a single trace attack. But if you take one step back and have a look on the key exchange again, and now on the left side, on the responder side, we have also a decapsulation step. And inside of this decapsulation step, as shown in detail below, you see in line 4, the decryption algorithm call, and inside of this decryption, we have a message decoding. And this message decoding is the inverse operation of the message encoding we analyzed, and we had a look on during the whole presentation, and our approach can also be applied to this message decoding step. And then in line 6, we have a re-encryption based on the Fujisaki-Okamoto transform to ensure CC8 security for the scheme. We have, again, then message encoding, and therefore in the whole key exchange, the very same message is processed up to 3 times if we consider that an adversary has access to both parties. And then an adversary would be able to measure all 3 traces and use them to increase the success probability. So we then can do 3 single trace attacks and can decide to a majority. How does it look like? So we do, this increases the success probability to the values you see now in the table on the rightmost column. And what you see now is that for all implementations we have seen here, except on the byte and bit level of random ordering, you have now a success probability of more than 70%. And only for the last approach, it remains nearly to random guessing. And therefore, this is the approach to choose. And additionally, if you want to keep an adversary in a single trace scenario, you can choose different but static randomization bytes for fetching the randomization variable inside of this countermeasure. So for example, you can take byte 0, as we have seen in the encapsulation, and then you can take byte 1 during the decryption, so in the message decoding, and byte 2 for the re-encryption and the message encoding there. And then we have 3 traces that depend on the very same message, but they are completely random, completely different ordered and completely different randomized, since they depend on 3 different bytes and 3 different randomization variables. And then you have cannot map them together, and you have again in a single trace scenario. So here are the references I used during the presentation, and thank you for your attention. And if there are any questions, please feel free to ask.
Thank you for the talk. There are already questions from the audience.
Okay.
Hi, thank you for the talk. I got very confused in the middle of the talk. What success rate are you measuring? Success rate of recovering a single bit of the key?
Can you please repeat it more louder?
Sorry. What success rate? What is the success rate that you are measuring? Because you said like 50% of success rate is random guessing.
Yeah.
What are you recovering? A single bit of the key?
Yes, this is the probability to extract a single bit.
Okay, right.
And if you want to extract the whole message, or you have to take this to the power of 256, or for 20 bit, the power of 20 bit.
I just got confused. I thought it was, for a while, I thought it was the success rate of the whole key. So I was like,
okay, no.
Okay. Any more questions from the audience? I actually have a question. So the standard countermeasure is, so the first countermeasure I think of, if I want to expect something, is masking. So this is quite different from masking. This is more like a hiding countermeasure. So can you combine these two? Can you use your approaches on a masked implementation to make attacking a masked implementation harder?
Yes. The most masking schemes do not consider the encapsulation, not the encoding step. So
it's in the re-encryption.
Yeah, re-encryption or in the encryption, the same. So yes, you can just process it in the very same way. You can just implement it and use the randomization counter, and can replace the original message encoding by this, and then you can do the very same as before, and just it does not affect it in any way. So
you can use your method on a mask implementation.
Yes, yes. You can do it to. You can just replace it.
Okay. Did you have a look at concrete masking schemes?
No.
One more question. I just had. Any more questions from the audience or online? No. There was a question. Yeah, there is.
Yeah, thanks for the talk. I also had a question about the success rate, actually, because SPA is usually done by just looking at the traces, right? So did you automate it somehow, or did you actually manually go to the trace, or how is it?
Okay, for all implementation, we measured a set of 8,000 traces. Okay, for the last implementation, we extended this to 80,000. and then we divided the whole set so into 4,000 traces where we built templates, and then the other 4,000 traces we try to classify based on the templates, and the success rate based on this classification, which if they was correct or not.
Okay, thanks.
I think there was another question somewhere.
Have you tried? So when you do the decoding, I guess you can try to decode multiple times the same ciphertext. And so you can average the leakage traces, and maybe you get a better estimate. Maybe you get a better success rate when you do that. Have you tried? Or?
So we only focused on the message encoding. Okay. And this is just an assumption if you have the same probability for the message decoding, but we didn't focus on it.
Okay, thanks.
I have one more question. So you implemented shuffling. How did you exactly attack the shuffling? Did you try to unshuffle it, or
no,
templates on the addresses or something like that?
We tried to use a whole trade, even where the patching of this randomization variable happened, but they were not as much leaking as they were selected as points of interest for our SPA.
Okay.
So yes, we take that also into consideration, but not too much into detail.
Okay. Any question? I think we have time for one more. Okay. If there are no questions, then let's thank the speaker again. But since please stay, there is a something from the chairs. I hand over to them.
So we already announced that you are the best paper student award. So this is your certificate. Congratulations. Thank you very much.
And as we are in Lübeck, you also get some Lübeck marzipan for you and maybe to share with your co-authors.
Yeah, of course. Thank you very much.
Yeah. Thank you.
And then this leads to the second keynote of CARDIS that will be given by Christine. So Christine is a researcher in cryptography. She has a PhD from Technical University of Eindhoven. And yes, his PhD thesis is entitled Exploring Mathematical Structure in Cryptography, and she continues on this subject in NXP now. She has published various papers on the different subjects of cryptography. And actually, there is only one in CARDIS. So this is probably your second talk in CARDIS. The first one was about kangaroo in side channel. And actually, on your website, you have a kangaroo, so you maybe have some links with kangaroo. But today, we don't have any kangaroos, I think. So we decided to talk about post-quantum crypto and the NIST competition. And now I will let you start.
Yeah, thank you very much, Vincent. I have one. Okay. There we go. Thanks for the introduction and welcome everyone, and thanks for joining. So unfortunately, I won't be talking today about kangaroos. I tried to work one in somewhere, but if you have a hint where I could have, then please let me know. Today I'll be talking about challenges of post-quantum cryptography, and specifically in the embedded world. And this is it's sort of an overview of all the challenges I've run into over the approximately past 3 years. I've been working on specifically implementations of post-quantum cryptography for embedded devices. And Well, in this overview, I'll cover many works which are written with many authors whom I'd like to thank at the start of this presentation. I should turn this on. Yeah. Yeah, so I'm just going to start from all the way from the beginning, even though the previous talks already gave some introduction on this topic. So currently we live in a pre-quantum world, where if Alice wants to talk to Bob, they can use an RSA or ECC key exchange to agree upon a joint secret key and have further secure communication. Unfortunately, there is a threat to this very sunshiny world, and that is the quantum computer. That's also already been mentioned before. So if it were possible to have what we call a cryptographically relevant quantum computer, so one that can break RSA or ECC, then an adversary can use this to take Alice and Bob's public keys, recover their private keys, and break this communication. Now, luckily, there are researchers like us who have a fix for this problem, namely to replace the ECC or RSA key exchange with a post-quantum crypto one. So now, instead of using some elliptic curve, Alice can say, let's use Kyber-Chem 768 or something similar, and the quantum adversary is thwarted. Now, a natural question to ask in this scenario is, when does this problem occur? And it's kind of a running joke in the community that for the past 15 years, people have been saying that there might be a quantum computer in 15 years. But this is, of course, well, not very useful if you want to prepare for this incoming threat. So in 2019, Mosca and Piani published a quantum threat timeline report where they tried to take a little bit of a more scientific approach. Namely, what they did is they contacted, I think there were 44 researchers that are top of the field in either quantum computing or quantum cryptography or post-quantum cryptography, and asked them when they would think is a likely timeline that such a cryptographically relevant quantum computer, so one that can break RSA 2048, would be a reality. And included was this graph, and it's kind of a complicated graph, but the idea is that from left to right, each of these 44 experts has one line drawn, giving an opinion on whether this quantum computer will be there in 5 years, 10 years, 20 years, etc. And therefore, a thicker line means that a lot of these lines of the experts are overlapping, and therefore they sort of agree that this is a good estimate. So what we see is that probably in 5 to 10 years, most of them agree that it's not very realistic that this will exist, while in 15 to 20 years, it's becoming like a 50-50 probability that there will be a quantum computer. And within 30 years, the general opinion seems to lean that it might be actually very likely that there is one. But even when knowing all these probabilities, there is still a chance that there might not even be a quantum computer, because there is still research to be done to overcome the last hurdles to get to such a large quantum computer. So maybe there won't even be one. And the point I sort of want to make here is that at least for many industry people, it doesn't really matter whether you believe in one or not. You can have long discussions on all kinds of physics that I personally don't know a lot about to get into this conversation. But what is relevant is that there are post-quantum crypto standards coming. And as soon as there are standards for some sort of cryptography, there will be people, products, customers in the world that will ask for the enablement of such post-quantum cryptography. So then whether or not quantum computers are going to be there is not really relevant. We have to implement post-quantum crypto anyway. And then, I mean, I won't talk, this is a very nice NXP marketing slide. But the point is a bit that given that these post-quantum crypto standards are on the horizon, the question what you can ask yourself is what is the impact on embedded devices? And we in the previous session already saw some impacts that are there on embedded devices. But maybe more generally, an embedded device is still a pretty broad term you can use. So if you look at the different applications, for instance, in mobile, it's generally important to make things small. Smaller is better. You can have more fancy things in your mobile phone and you can sell more phones, so that's better. While, for instance, in automotive, it might be easier to take a slightly larger chip to cover your post-quantum crypto needs. On the other hand, in automotive and, for instance, industrial, it's very important that there is very little latency, since having a signature fail or being late can have huge impact either on safety or, I don't know, in case of an industrial, in case of the industrial contest, it can lose you a lot of money. While this is maybe less critical in the mobile world. So now that I sketched the context a little, what am I gonna talk about in the remainder of this talk? Well, it can be sort of summarized in challenges, but because I wanted to avoid just going through a laundry list of problems there are when implementing post-quantum crypto on embedded devices, I kind of put it into three categories. Namely, one, I will first talk a bit about general post-quantum crypto challenges. Then some challenges that exist in stateful hash-based signatures, where I will, of course, also talk about what those are. And then the last topic is focusing a bit on challenges in lattice-based cryptography schemes. And ending with some concluding remarks. So first, general post-quantum crypto challenges. And the challenge I mainly want to talk about here is that of migration. So what is the problem with migration? Well, migration is hard and it takes a long time. And there are in cryptography many proof points that show that this is the case. So for instance, for the hash function MD5, already in 1996, a first collision was found, well, on the compression function of MD5. And what followed were 16 years of attacks while this primitive was still being used until an actual certificate forgery happened. And by then people thought, okay, maybe we should really not use this anymore. Similarly for SHA-1, so there, it was in 2015 that the first warning flags went off that maybe there might soon be a break coming, and it was not advised longer to use it, and now we are 16 years further, and at least I still see applications of SHA-1 popping up here and there. Then another example is that of RSA and ECC. So ECC, elliptic curve cryptography, was discovered in the 80s as a use in cryptography. It was faster, generally smaller than RSA, and still we are now 20 years later, and it's, I mean, there are many places that still are diehard users of RSA. So these are all examples where there wasn't a real hurry, or at least you can argue that for many devices now using SHA-1, since the current collision attacks aren't really scalable, there's not really a massive panic happening to replace these devices. But an example I heard recently was on Y2K. So if I look around the room, I think most of you will remember this, but just for context, in the years 90s, in the 90s, it was discovered that there would be many devices that would have a problem around the year 2000 because their data field was implemented with too little bits to store the entire year, so 1999, but just stored the last two numbers, which would mean that once we roll over to the year 2000, all these devices would claim they are in the 1900s and a whole slew of problems would follow. Now, this is a problem that's relatively easy to solve. You need some extra bytes in the data field. And seeing, as we saw this coming, companies threw billions of dollars at solving this problem. And yet it still took over 6 years to solve most problems. So even here, where there wasn't hurry, it's such a challenge to update so many devices, and now there are even more in the world. So if we optimistically think migration to a new crypto standard might take 10 years, but if there is no real hurry, so there is no known quantum computer yet, maybe 20 or 30 years is a more realistic estimate. Now, this long migration time is not for all products an issue. So if we take the positive note and say we can migrate in 10 years, and a cryptographically relevant quantum computer will take about 25, then there are actually many IoT devices available that don't really see it as a threat yet, because the shelf life of your average IoT device in the home will be less than 10 years. So even if they're developed now on the shelf in 2 years, you expect nobody to be using it anymore in 12 years, you can ignore the quantum threat for now. For some applications, it might just fall outside of the threat model. So if you have an application where it's very easy to physically go there, physically replace the device or update it, then you could start, you can think about putting post-quantum crypto in there now, or you can think, well, in my threat model, I can also, if I hear that a quantum computer is now in existence, bike there or drive there and replace it physically, and then the problem is also solved. But there are applications where the impact is huge. So the default example is, of course, automotive, where cars being designed now will drive around outside in, let's say, 5 years. And, well, maybe not all cars, but most cars will be there for 20 years to come. So then you have a device that's kind of hard to update since it's no longer in your, well, in the maker's actual presence. And it's out there in the field for 25 years. So then you might be thinking about updating it. Yeah, and then I've been focusing mostly on the very simple thing of we have one cryptographic primitive in a device and we want to replace it by another one. But there's actually many more problems that come up even after switching out just the cryptographic primitive. There is more things that need to be thought about. So one thing is, for instance, having hybrid encryption, where you're not only using post-quantum crypto, but also pre-quantum crypto together. Sounds like a pretty good idea, but it will add issues, because then you first have to migrate there somehow. You have to define, well, which combinations to migrate to. And after migrating there, at some point when there would be a quantum computer, if this does become a reality, you have to make another plan to transition out of using pre-quantum crypto. And yeah, there are, so also in trust provisioning, so how to get these post-quantum secrets into all the chips or other devices, that's something that needs to be thought about and might need some revision in infrastructure to make that happen securely and safely. Then you haven't even talked about versioning and key identification yet. So it was already mentioned that this NIST not competition had some rounds, and over these rounds, popular primitives like Kyber and Dilithium, there are many versions running around with different parameter set, different implementations. And there are now already issues where different implementations cannot talk to each other anymore because they are using a different version. And well, to make sure that all these versions have to keep talking to each other will be a challenge. And then lastly, I put patents in the list. So this is a bit of a controversial topic, maybe, but there are some patents out there of which could be argued that they might threaten some post-quantum primitives, and to figure out what the impact of the world is on that, it will also just take more time. So that was on the general challenges. Then we're swapping to the next laundry list of challenges, and that's regarding stateful hash-based signatures. And the main challenge in these type of signatures is the fact that they have to manage a state, and that's what I want to talk about in the next 3-ish slides. A hash-based signature scheme, and more specifically a stateful hash-based signature scheme, is actually based on a pretty simple premise. You take one-time signature key pairs, usually hash-based one-time signature key pairs, where generally you would have to make a secret key, publish a public key, and then you could sign one message with your public key. So you take that paradigm, and instead you take the public keys of multiple of these pairs and hash them into a binary Merkle tree, like it's depicted on the top left here. And the idea is then that if you now want to sign with the scheme, you pick a pair to sign with, and you keep track of which key pairs you've used, and use each pair only once. And this is very important, because if you reuse a pair, well, the name one-time signature sort of gives it away. You reduce the security by reusing it for multiple signatures, and if you use it for enough signatures, you even break it fully. Well, this is a nice scheme, since it's already sort of standardized. NIST put out a standard, a special publication, 800 and 208, to already specify which parameter sets should be used, how to implement it, what not to do. And this is very much supported by government agency like the US agency NIST, which was already mentioned, as well as the German BSI, for instance. And the reason that it's well liked is because it has a rather simple security basis. So in these one-time signatures, what basically happens if you have the secret key, a bunch of hash functions are applied until you get to the public key. Then all these public keys are again hashed a bunch of times until you get the public key of the scheme. So the reliance in this scheme, or the security reliance of this scheme, is mainly on the security of the cryptographic hash function, as well as maybe the pseudo-random function, pseudo-random generator. And these are things that are quite well studied compared to lattices or code-based or some of these other things you will see. These are less well studied in the recent years, while there's been many papers on hash functions. So what's this state that you need to manage? I put it in as an example where you have 8 key pairs and 1 public key. And what you do is, if you want to sign with your first one-time signature key pair, you sign with your secret key, and then that's part of the signature. And then along with that signature, you also compute these nodes in the Merkle tree. How exactly you do that, I won't go into the details. But you also compute this. And then your entire signature is the state, so which number signature you're using, the signature of that state, along with those red nodes, which are called the authentication path. Now, if you continue this, you can sign with the second one. You have to update the authentication path to send the right nodes along. And you can continue this process for all keys until you reach the last key, where you can do the last signature. Now, why do I call this slide a hash-based hassle? Because there are some challenges you can run into when doing this. And the first one of this is maintenance. So you have to maintain the state. So you have to have some sort of non-volatile storage where you can securely store this. As well as, yeah, you have to keep track of which of these authentication nodes to use. This also means that because the state needs to be maintained, and all these authentication nodes need to be maintained, the scheme is not very well suited for very high-speed applications, since maybe an example where the speed would become too high, the state is not updated correctly, and again the security goes down. Then the second thing you need to deal with is this depletion. So in this scheme, after 8 signatures, you cannot sign anything anymore. And now in realities, these trees are of course much bigger, and you can sign many more keys, and you would choose a tree size such that for your use case, you likely always have enough keys. But there are also many use cases where even in the case that you likely have enough signatures to last a lifetime, a backup plan does need to be in place in the weird case that, I don't know, a DDoS attack happens and all your keys get depleted. So you do need to think about a backup plan here, and that's a bit of a hassle. Then thirdly, I wrote down scheduling. So to compute these nodes every time you swap key, sometimes this is rather easy. So if I go from the 7th key to the 8th key, only one node swaps. While if I go back a little, if I go from the 4th key to the next one, a lot more nodes swap. And this means that there's actually more effort for some keys than for others. And if you want to somehow make sure this effort is even, you have to use special algorithms to determine which computations should occur when, and the scheduling, well, it can be quite a hassle to implement. And then the last thing I wrote down is that of fault attacks. So maybe a positive thing first, since this is mostly based on hash functions, it's quite well resistant against many side channel attacks. But since we are looking at one-time signatures, actually against fault attacks, there needs to be extra care, since this state, if it's faulted to something you don't want it to, and the same key is being reused to sign multiple messages, the security of the whole scheme can go down. So this is definitely something that needs to be taken proper care of. To end on a positive note, though, it is a nice scheme since it is already standardized, and at least at NXP we like standardized things. It has a reliable security in what are the hash functions. And the third thing, there's lots of hashing happening, and that, I mean, that's a lot of work, but at least the current hardware acceleration already has acceleration in place for all these hash functions, or at least a subset of them that are standardized. So that's nice that the hardware is already in place to do this somewhat effectively. Now, if we take a step back and look at the embedded use cases, then these stateful hash-based signatures are quite okay for some use cases that you see often in the embedded world. Namely, both in secure boot as well as over-the-air updates, you have a situation where the state can be managed on the cloud side, so that's where you have more resources to deal with the state management, as well as there are not too many signatures happening at once, so you don't have this issue of running into problems with updating the state as well there. So for those use cases, this scheme is kind of good. However, then we still have the other side of the coin, namely this does not do anything for digital signatures in high-speed use cases or for key exchange, like for instance, secure element communications or trust provisioning. And that's the topic of the, let's call it, second half of my talk. Maybe I'm not sure if it's inconvenient, but if there is a question now, since I'm swapping topics a little, does anyone have a question? No? Okay, then I will just continue. So the second part is on those key exchange mechanisms or digital signature schemes where alternatives that are not stateful And I call this part specifically lattice scheme challenges because for embedded context, lattices seem like the better candidate to use. They still have large key sizes, but they're not ridiculously big, and the speed is okay. So in that respect, that's why we sort of focus on this. But I'll let some of the other flavors go in there too. So Georg already mentioned the NIST competition in his talk, but maybe to give a bit more detail. So in 2016, NIST put out a call for proposals for post-quantum key exchange or key encapsulation mechanisms and digital signatures. And at that time, about 69 candidates were submitted, and in different rounds, more of those are broken or deemed somewhat, well, not good enough to use in many use cases. And then in July 2020, we were left with, on the left-hand side, 7 finalist candidates that are likely to, well, a subset of them is likely to be standardized around 2024. And on the right side, 8 more, what they call alternate candidates that could be standardized at a later time, because, for instance, they have some schemes that are, for some use cases, particularly good, because they have really small ciphertext sizes or are really fast, but could do with some more cryptanalysis before being standardized. As well as some of these alternate candidates are more of a backup. Like if one of these left schemes turns out to be trivially broken tomorrow, then at least there are some backup schemes already being considered. Now, and that's then also where the first challenge in this topic lies. From an embedded perspective, although you can design very nice hardware components for all of these schemes, we cannot start inputting all those components into chips right now. That's simply not feasible to prepare for all of these. But luckily, as I already mentioned, this challenge sort of solves itself naturally, since NIST promised that by the end of this year, likely start of next year, a first subset of these will be chosen to be standardized. So likely 1 or 2 key encapsulation mechanisms or 1 or 2 digital signatures will be picked to start to write down this long-term standard of 2024. And now, of course, it's one option to do absolutely nothing until that happens. Just wait till NIST makes their picks and then start working on this topic. But there are, of course, some things you can already generally do now. And one thing there is to look at more general challenges. So, for instance, here, for the very general challenges, which are the first topic, you can look at things like key sizes and stack usage and see how current chips stack up against qualifying and being able to run those. And if you had asked me like 6 years ago what will be the problem with post-quantum crypto, I would have said, well, it's probably slow. But it turns out that this is actually not the main challenge. So if we look at the speed of the CAM candidates, then and compare to a key exchange with elliptic curve cryptography, I mean, it's a bit of an unfair comparison since this is an entire key exchange and this is just the encapsulation. But at least you can see they're in the same order of magnitude. So yeah, it might be slower, maybe in some applications even faster, but at least it's not a huge problem. And for digital signatures, you sort of see the same issue. Okay, Rainbow is this third candidate that might not be a candidate anymore, so let's ignore that. But even Rainbow, I mean, it's a lot bigger, but it might still be feasible for some use cases. But especially the lithium and Falcon are actually quite close to the elliptic curve use case yet. So speed actually turns out to not be the biggest challenge. what does matter is size. So when NIST put out their focus for research, we already saw that before as well, that the M3, the M4, and the Arctics 7 are the main focus. But actually, if we look in the embedded world, then the M4 is actually already quite high-end and can be considered quite high-end. And the typical maximum stack requirements for the more general applications are actually only 1K or 2K or 4K. And if we now compare that to the stack requirements for the various schemes, we see that ECC fits quite easily in these requirements. Kyber might fit, depending on your luck, but especially Sabre and Entru, with the slight remark that this might be unoptimized and probably there's a bit to be shaved off here. That's quite an issue. And then things can be slow or fast, but it doesn't really matter if it doesn't fit. Then you can simply not run it. And you see a similar story in the key sizes. So in embedded devices, usually smaller is better, and you want to save every byte. But if we now compare the secret key sizes of RSA and ECC to those of the other schemes, then we see that for the hash-based schemes, it's still sort of okay, but these again don't work for all use cases. But especially if we go up to the key exchange mechanisms, there's a definite order of magnitude difference. For some of these schemes, you can do something to mitigate this. So for instance, at least for MacLeese, I know there is options to stream in and stream out the public key, so you don't have to process all these bytes as once, but you can process them in blocks. But still, that's of course also a downside that you don't necessarily want. Yeah, so those were the very general lattice considerations. Then next I want to talk a bit about the hardware challenges. So I should note here that I'm not an expert, full expert on hardware, so correct me if I say anything wrong. But if we look at a block diagram of what a chip looks like, here is a very specific chip that is pretty high-end for audio, voice, and video recording. We see it has many capabilities, but if we then zoom in on the security part, we see it can do some things already that are very useful. Namely, we see the SHA-256 in there and some symmetric speedups, and that's of course still useful in a post-quantum world. And particularly SHA-256 is one of the standardized hash functions for these stateful hash-based schemes and can therefore very easily be reused. Now the RNG is also of course very useful for any scheme that needs some randomness. We have some eFuse key storage it's generally useful for any scheme, although it might be too small for most post-quantum schemes right now. So many useful components, but definitely no components that can specifically speed up code-based crypto or lattice-based crypto or multivariate crypto or whatever kind of post-quantum crypto you like. And as I mentioned before, we cannot simply start integrating all of this until we know what will be standardized. What we do know, however, that specifically for lattice chems, Dustin Moody in the last round 3 status update has mentioned that there is some sort of main decision point where it's very likely that one of the lattice chems, so Kyber, Entru, or Sabre, will be standardized. And similarly for lattice signatures, Dilithium and Falcon are both lattice type signatures, and likely one of them will be standardized. So it is quite likely that at some point in the future, chips will need to support lattice-based schemes. And if we now look at the main operations, we saw on the previous slide that there's an RSA accelerator in there. What it does is modular multiplication, make that really fast. Of size, well, it can differ a bit, but maybe n is about 3000 bits. It can also speed up ECC, where the main computation is elliptic curve, scalar multiplication, which are multiplications on the elliptic curve over the finite field of size p, where p is 256 bits. Now, if we compare that to the main operation in lattices, there, instead of having modular multiplications or elliptic curve scalar multiplications, we actually have polynomial multiplications. And these polynomial multiplications occur in some ring. So I wrote down one here. This differs a bit depending on which scheme you're looking at. But generally, Q is about 16 bits, N is 256 for, well, at least some schemes it can go up to 1000. And operation is polynomial multiplication. And now the question is, we have a coprocessor, a hardware block present in chips to speed up these things. Can we use this to speed lattice-based encryption? And now we don't expect the reuse of these coprocessors to be as fast as building dedicated hardware blocks, but maybe it's just an intermediary solution until then. And the answer is, well, yes, you can. Actually, already in the late 1800s, it was observed that you can do this. And the idea behind this paper by Kronecker is, I will show it by a small example. Of course, in reality, we have much bigger polynomials. But suppose we want to multiply f and g in the polynomial domain. Then instead what we do is we put those polynomials in the Kronecker domain. And we do this by taking a valuation point, here as an example 100, and evaluate both polynomials at that point. And now we can multiply these large numbers, and what we actually get looks very random, but if we do our basic algebra, then this is actually the polynomial f times g evaluated at 100. And although these numbers look sort of random, it turns out that if you look at what is there, the last part, last two digits are actually 5. And if we look at the top, the coefficient of f times t of the monomial x to the power 0 is actually also 5. And we can continue this. If you look at the monomial x, then this 16 comes back, etc., 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 etc. And you can actually read off the result of the multiplication by looking at the multiplication of these large numbers. And that's actually great, since that's what we saw on the previous slides and the RSA coprocessor can actually do. So in this way, you could reuse a large integer arithmetic processor to do some polynomial multiplications. Now this was already first applied to Kyber by well, Thomas and co-authors. However, they ran into the fact that because Kyber specifically is built around this number theoretic transform, that it's hard to use Kronecker substitution to improve performance, because you first have to take the polynomial out of entity domain before applying this technique. And then in a paper last year, we tried to generalize their idea and came up with Kronecker Plus, which generalizes it in the way that not only can you evaluate at a large number and multiplies those, but you can use the underlying ring to do more fancy things. And I won't go into details how that exactly works. I recommend to watch that video. But I try to capture the idea here in this table, that if you do general Kronecker substitution for Saber and you input these large numbers, you get about 8,000-bit numbers. And if you then multiply the two polynomials with schoolbook, it takes one multiplication. While if you have a smaller width multiplier, you have to split these large numbers up again. So since schoolbook is a quadratic type of algorithm, if you have the multiplier size, you need 4, 16, 64, etc. many multiplications. Now what Kronecker Plus does as a generalization is that for one parameter, you can still do basic multiplier with 8192, and this is then also coincides with the work of this B. And you can do it in one multiplication. Then you can generalize by, instead, if you have a multiplier width of about 4000 bits, instead of needing 4 multiplications, this new algorithm only requires 2. And this was also an idea that is basically one that's already given by Harvey in the end of the zeros, which it involves splitting the domain to do things more efficiently, but then you need only 2 multiplications. And then this algorithm generalizes this further. So for instance, if you have a multiplier width of only 512, instead of needing 256 multiplications, you only need 16. And this is then nice in the chip world, where maybe different vendors have different RSA coprocessors with different multiplier widths, and you can use this algorithm to split it however you want. So then the last topic I want to talk about is that of side channels. So with all these new schemes, there is new side channels. Well, maybe not new side channels, but at least new targets to target with the existing ones. And since there are new targets, there also need to be new efficient countermeasures. And the last topic I want to talk about is a bit of this. So as I mentioned now a few times before, the lattice schemes use an underlying ring, and this is very nice since you can speed up multiplication by using all kinds of nice algorithms like Karatsuba, Tum-Cook, Kronecker Plus, or the number theoretic transform. And this multiplication is present in all these lattice-based schemes. But at the same time, this same structure can be used by attackers. And this is, first of all, theoretically a challenge. So I think there is still generally progress being made in analysis of these underlying rings. How can they be used by attackers? How do they impact the security? Talking about this requires a lot of mathematics, which I will not do now. But on the other hand, which is more of interest here, it also opens up the world for new side channels. And to talk about those, I first put the same picture we've seen before. So this is the inverse number theoretic transform. And as also mentioned in talks before this one, is that the idea is that by working in this specific ring, it has a nice property that it has an nth primitive root of unity, for Kyber at least. I note that generally an entity would require actually a 2-nth root of unity, but again, let's ignore that. And the idea is that if you now have a polynomial on the right-hand side, you can, by these efficient butterfly operations, put it in the entity domain, where multiplication of polynomials is a simple pointwise multiplication between vectors instead of a complicated cross product. You can do the multiplication there and then turn it back again. So this is very nice, very fast, very nice structure, but it turns out that you can also use this for attacks. So already in 2017, Primas, Pessel, and Mangard, this is a picture from their presentation, I should say, presented an attack that attacked all these different intermediary values that are all leaking power traces, and then observed that these leakages are of course not independent. So the leakage here is depending on the one there and there by way of an addition. And in that paper, they showed that even though it's very hard to just write down a complex joint distribution with all these leakages to recover the secret key, what you can do is apply belief propagation. And again, I won't go into details how that specifically works, but the idea is you iterate through possible values until you find an approximation of the complex joint distribution to recover the key. And then 2 years later, they also discovered that you can make this even more practical. And then last year, in a paper with many co-authors, we showed that you can even improve this if you combine it with a chosen ciphertext attack. So how that works is that if you can somehow in the entity domain force that some of these values in the entity domain are actually zeros, then you don't only have that these values in this column are dependent on the values in this column, but you even have that this entire block of leaking values only depends on one value in the entity domain. And this allows it to be even faster to apply belief propagation to recover this complex joint distribution and have faster convergence of the belief propagation. So the point I'm trying to make here is that this entity is very nice. It makes things much faster when implementing things in software or hardware, but it actually also gives attackers some tools to work with. Then another challenge is the CCA transform. So I'm very much simplifying what happens when Alice and Bob are trying to encrypt using, for instance, Kyber or Saber. But what happens generally is Alice takes a message, encrypts it to a ciphertext, sends it to Bob, who then decrypts it with their secret key to get the message back. The problem is that such a scheme, whether pre-quantum or post-quantum, is generally not in CCA secure. Now there's a solution to make it in CCA secure, and that's to apply a CCA transform. And the CCA transform of choice for post-quantum schemes seems to be the Fujisaki-Okamoto transform. And the idea there is that when Bob decrypts the message, instead of just stopping there, actually re-encrypts it to get the ciphertext. And this has the following goal, namely that if somebody messed with the ciphertext, so for instance flipped a bit, and whether that led to a faulty message as well, Bob can detect it by re-encrypting it, and then if the resulting ciphertext is not equal, then we can assume that this original ciphertext had been a chosen ciphertext attack, let's say. Now, this does not fully, this works in theory, but in practice there is still something an attacker can do. Namely, if this ciphertext is changed compared to this one, so a bit is flipped, then an attacker can attack the resulting message with a power attack or something to detect whether a bit has been flipped there as well, and hopefully derive something about the secret key. And now the downside of this CCA transformation pops up, since this message is not only here, it actually propagates through this entire re-encryption to C. So an attacker cannot only attack this point, but can attack many points in this re-encryption. And even can combine the results of all these power attacks and try to derive whether only one bit was flipped. So this is actually quite a powerful attack. So what can you try to do against it? We've heard hiding in the previous talk, or masking. But this attack is actually so powerful that you would likely need not a first order defense masking against it, but multiple. So you need 3, 4, maybe 5 shares to make sure you are defending against this attack. And these shares need to be in this entire encryption behind it. And this is the last challenge I would like to point out, since these new schemes also means new masking techniques. So on this slide, we see a sort of simplified representation of the Kyber encryption, or decapsulation to be precise, actually. And we see some blocks that are relatively easy, like some don't need to be masked. Some are linear, or in case of the decompress, almost linear blocks that we know how to mask efficiently, and this happens by known techniques. Then there are some blocks, and here in light blue, that are symmetric primitives that we also know how to mask. It's relatively efficient, so these blocks are also kind of easy. But then it gets harder, because for instance, for the sampling box, the CBD, there are known techniques on how to mask these, but they're already getting more expensive. And the higher order you need to protect, the more expensive they become. And then the last blocks are these compress Q function and the decompress comparison. So these are new blocks. And we still see many advances in how to mask them better and faster, using less randomness, etc., etc. But these are still improving, and especially for high orders, they're still relatively expensive to mask. So if we do have to protect this CCA transform in hardware, it will likely still be quite expensive. So that leads me to my conclusions. Yeah, so the point I started with is, for me, or more generally, work and research we do at NXP, it's kind of irrelevant if the quantum threat is becoming a reality. As soon as there are standards, PQC standards to adhere to, they will need to be implemented in practice. And then in this talk, I covered many challenges. I hope it didn't feel too much like a laundry list, but it's not even comprehensive. These are challenges that I and colleagues ran into over the past year, but I did not cover any challenges in non-lattice NIST candidates. I did not cover too many challenges related to hardware, software implementations, or even their co-design. I also didn't mention anything on the protocol level, so how to update all these schemes in practice, and probably I didn't cover much more. So the point is, I already had a long list of challenges, but likely there are many more to be found. Yeah, and then I would like to end with that hopefully some of these challenges will be resolved in the next years. Possible research directions are always to look at more side-channel fault attacks on any PQC scheme, because if we don't know about them, we cannot defend against them. And then also inherently faster countermeasures against these attacks. Then some research has been already going into alternatives for this Fujisaki Okamoto transform. But that's also a valid direction to see if there's some alternative to make things easier to defend against. And then lastly, something I did not really mention in this talk, but in the embedded world, often on device, you perform the verification and not the signing, which means that if there for certain schemes are trade-offs to be made where the signer can be given some extra computation load, which is likely happening in the cloud anyway, while the load on the verifier can be lightened, that's also a research direction that I'm very much still interested in. Yeah, so that is it for me. Thank you very much for listening and staying awake during this talk. I will take any questions now, but if you think of any questions later, my contact information is down here. Don't be scared by the different last name. It's really me. And I'm always open to get an email with any question. So thank you very much.
Thank you very much for the presentation. That's nice, and there is a lot of subject which is not too broad. Do you have any questions?
Thank you for the presentation. I was thinking about these hash-based signatures, and let's suppose that you want to use them for something like a firmware update, in which you have to, I guess, verify the firmware. Does it mean that in the verification you have to store some extra state which keeps track of which path is used? Is this correct?
No, so that's actually another nice thing about these stateful hash-based signatures, is that the state maintenance is wholly on the side of the signer. So the verifier can, based on receiving the state, the signature, the one-time signature, and the authentication path, simply compute whether it's correct.
But then if the verifier is not keeping state, can't you just do a replay attack by just looking at a one valid signature? Maybe I'm just completely misinterpreting how the signature algorithm works. But if there was a path, as far as I remember, and then you have to hash your message with the last root, last node. This is the way it works.
So I can, I think, go back. I mean, it's a lot of slides and it's PowerPoint. So. Yeah, so how it generally works is what the signer, you have the private key, the public key, and what the signer does is they compute a signature with this key pair, and then also compute these nodes, and they can compute this because they have all the secret key pairs and they can also compute all nodes. Well, for the verifier, all they have to do is they pretend like they verified a one-time signature. So verification of this one-time signature leads to this public key, but then this public key is not really public anymore. Since in this Merkle scheme, you don't want to publish all these public keys, but just this one. So what the verifier does instead, take this public key, it gets hashed once to make it smaller. This is the value in here. And then you can pairwise hash. You hash these two together to get that one, hash these two together to get that one, then hash these two values together to get that one. And then verification occurs if that matches the public key of the scheme.
Right. So in the signature, you have this intermediate nodes as an additional information. And then if there's a replay attack, you would again provide the same nodes. But then you have to break the one-time property of the signature scheme.
Yeah, so you can replay the same signature. It will have the same nodes, but then this part, you cannot change the message because that would include making a forgery of a one-time signature, which is also deemed to be secure.
Right. But then you already have one signature, and then you're trying to make another one. And one-time signature implies that you can only use once.
Yeah.
Okay. And then that also requires some additional post-quantum guarantees, or for that scheme, because that's a signature scheme now, right?
Yeah, so it is a signature scheme, but since it's based on all the hashes in there are SHA-2 hashes, and SHA-2 is deemed to be post-quantum secure, so therefore the scheme is deemed to be post-quantum secure.
Do you think there is any chance that NIST will take side channels into account?
Yes, there is a chance. If I look at what's been happening recently, I think there are factors that are more taken into account than side channels. I think, I mean, I haven't asked them, but I think the NIST way of thinking is currently that, okay, if we just choose a theoretically secure scheme, then those side channel countermeasures will be developed by many smart people later. So I think it would be taken into account if it trivially breaks something or something, but that won't ever be the case, I guess. So I think no, they won't take it into account.
You mentioned the issue of implementing the FO transform securely. On the other hand, when we look into other schemes like elliptic curves, there's also the challenge, for example, in ECDSA, that the ephemeral key should not be reused, and there should be no bias. So other schemes also are quite annoying when implementing them. And maybe can you give your view? How bad is it? Is it just as hard and as bad as with the others, or is it a new dimension of complexity?
Yeah, that's a good question. So I'm not exactly an expert on all the problems you ran into with ECDSA. I know when initially looking at this and running estimates on signal ratio, signal to noise ratio, initial estimates are looking, or at least the hope was initially that first order, maybe second order masking would be enough. And then I guess the estimates indicated that likely that's not enough. And whether more annoying or less annoying than in the ECDSA case, I can't really say. Let's say that it's surprising, or it surprised us how annoying it turned out to be, and that's why we noted as well, isn't there an alternative to do this, because this will be really expensive.
Thank you.
I guess it was essentially the same question, but just maybe reformulated. You mentioned the leakages in the entity transform, which is really hard to mask, and, compared to ECDSA or other standard. I mean, are the orders of protection significantly higher that you need now, or is it?
So for an entity, I'm not sure. As far as I know, that's kind of okay to mask, since there's a lot of linear operations happening in there. So the entity is, I guess, not the main concern. But there are more dependent leakages to be found. I guess with my limited knowledge again on ECDSA, I would compare it to taking straightforward implementation and then applying something like a sliding window method, which then might be faster, but it also gives more dependencies to a side channel attacker. So I guess it's always a trade-off. I don't necessarily think this is something you should immediately fix. But it is a good thing to be aware of, that all these optimizations happening left and right, they might also cause issues later. So maybe you don't want to over-optimize these schemes.
Okay, one more question about slide 30.
Sorry, which?
30. 30.
33. 33.
No, 30, just only 30.
30.
Yes.
So yeah, I really like PowerPoint, but this is just yeah.
Okay, here why we cannot, for example, apply the normal technique of message MAC, for example, the message with the hash. Why we need to use the cipher again for doing this kind of integrity check regarding post-quantum?
That is a good question. I'm guessing that has to do with the security proofs that analyze it, but I'm not 100% sure.
Because based on your slides, the hash is visible, the hash, secure hash against post-quantum adversary. So why we use, my question is just why we use encryption again here? Maybe later, not today the answer.
Yeah, so I'm not sure about the answer. I would have to rethink about it more clearly, yeah.
Okay.
I think it's because we are in asymmetric setting, so you cannot MAC. I mean, both parties do not share the same key, so you cannot MAC the message. No, I mean, one party has the public key and the other one the private one. So, I mean, you do not want to put the key you MAC above. I mean, we can discuss that offline.
Thanks again.
So we have a short break now and we'll continue at 5. Thanks.
Okay, so yeah, welcome back from this coffee break. I hope you all have your coffee and you can still stay awake for the next session. So yeah, welcome for the second session of CARDIS, and the title of the session is Fault Attacks and Reverse Engineering. And for this session, we will have two talks. And the first one is called Multi-Spot Laser Fault Injection Setup, New Possibilities for Fault Injection Attacks. And the speaker is Paul Grondam. So the stage is yours.
Hello, thanks for the introduction. It's nice to be here with all of you. Please forgive my accent. I will do my best. My name is Paul Grondam. I'm currently working at the French Hubert laboratory. With the Chimal laboratory and AlphaNov, we worked on a new setup for laser fault injections. The novelty is these achievements lies in the setup we built to make 4 lasers work together. We will see that it brings us new possibilities for fault injection attacks. This presentation will focus mainly on the new setup and the associated new possibilities. So before starting, let me redefine for everyone what is a fault attack and a fault model. A fault attack is a technique that consists in producing a fault in a system. Their purpose is to cause unusual behavior in order to extract information. As an example of fault attack, we can find clock glitches, electromagnetic waves injections, heating, power glitches, and laser injection. In this presentation, we will only focus on laser injection. A fault model is an abstract representation which makes it possible to predict the impact of the fault on the overall operation of a circuit. Existing models for laser fault injection are defined thanks to direction, cardinality, and repeatability. For example, we can find fault models which are only monobit bit set with a repeatability of 100%, or monobit bit flip with a repeatability of 10%. But as we are using 4 laser sources, we needed to add 2 more features to this model, and these are contiguity and time dimension. To illustrate the contiguity feature, I will take 2 examples. For instance, the kind of fault you can see on this slide can be done with only 1 laser if the spot is big enough to target 2 bits. However, the second one cannot be done with only 1 spot, with only 1 spot at a single time. To illustrate the issue we have if we use 1 single laser, let's talk about time dimension. So we made the hypothesis of a chip which has 2 millimeters on each side and a device running at 10 megahertz, which is a slow device. For instance, we target 2 elements that are distant of 10% of the chip, or 0.2 millimeters. Because of the speed at which the mechanical system can go and the location of the 2 strikes, it takes 0.01 seconds to move the laser, which is 100,000 clock periods. Because of this, we either have a constraint on the maximal distance we can have between features, or we cannot inject different fault close in time. So I will describe you the setup with 4 lasers we use to inject fault this way. So this setup is built by the French company AlphaNode. We can find two monomode lasers with a wavelength of 980 nanometers, which are linearly polarized but perpendicular. We can also find two monomode lasers with a wavelength of 1064 nanometers, which are linearly polarized but perpendicular. The polarization beam splitter cubes are reflective for one direction of polarization and transmissive for the other one. It's a combination of polarization. The dichroic mirror combines the laser beams of different wavelengths. It is reflective for the 980 nanometers and transmissive for the 1064 nanometers. In this case, it is a combination in wavelengths. To illustrate what I just said, the laser from the top goes like that, go like this. The laser from the top right sources go like that. And here are the trajectories from the two last laser sources. Here is a picture of the setup we just saw. We can see the 4 laser sources. The two on the right are the 980 nanometers wavelengths, and the two on the left are the 1064 nanometers wavelengths. The red line represents the optical path of the beam. We can also see the device under attack. Here are the 3 objective lenses available, 2.5, 20, and 50. Finally, there is a camera which allows us to see the circuits and the spots. So we managed to build a setup where the 4 laser sources are independent in time and in position. The trigger signal can be shared if we want to target 2 different positions at the same time. However, we remain limited on the distance between the spots. For each objective lenses, we have a different field of view and a different minimal spot diameter. Here is the principle of an attack. First, we have a computer which controls all the elements. It sets the positions and the current of the laser sources and the delay between the raise of the trigger and the shot, as you can see in blue. The chip whisperer is used to program and communicate with the hardware target, the green arrow. The trigger signal is generated by the target and sent to the function generator. You can see it in yellow. The laser sources are controlled by the function generator. This corresponds to the orange arrow. To finish, the laser shots and the communication between the hardware target and the computer in the other direction. We choose to target a 32-bit microcontroller with a 128 kilobytes NOR flash memory. When performing laser fault injection in NOR flash memory, we do not fault the memory elements, but only the readout circuit. The data stored in the memory is still unaffected by the fault. Moreover, we only do bit sets. We corrupt a 0 into a 1. If you want more information, it is well explained in the article on the bottom of the slide. The chip is open on the backside to have access to the bulk. We first need an infrared picture in order to locate the flash memory inside the chip. You can see this picture on the bottom right of the slide. Now, I will deal with the experiments done and the results obtained with the setup we have seen. The first source code set an 8-bit register to 0. We raise the trigger signal before the instruction and lower it after. At the end, we read back the content of this register. We run the flash memory along the length with a step of 45 micrometers. Here you can see the picture of a part of the flash memory that we attack. You can see 3 spots. As you can see on the last line, there is not only zeros as we asked with the previous code, but there is 3 bits that are set to 1. If one spot moves, it targets a different bit of the memory. We can see the same thing with 4 spots. So, to conclude this experiment, we perform simultaneous non-contiguous single-bit faults on a move instruction, which loads an 8-bit value in a register. To do the fault you can see on the bottom, we need to place the 4 laser sources at 90 micrometers distance from each other. In this example, we do not change the operation performed, but only the operands. So now that we inject a fault in a move instruction, we tried something more complex. We try to inject faults in a for loop. On the one hand, we inject fault at the incrementation of the loop, in the first red arrow. By doing this, we aim to skip iteration of the loop. In order to see our impact, we compare the number of iterations actually planned with the number of iterations actually performed. In assembly lines, this corresponds to this scheme. On the other hand, we inject fault at the exclusive OR operation, as indicated with a second red arrow. We aim to transform the XOR operation into an add operation. In order to see our impact, we count the number of times the XOR operation has become an addition. This corresponds to this line in the source code. We can see in the assembly lines that only 1 bit change between XOR operation and an addition. These experiments need to target 2 different positions really close in times. That's why it's needed to have a multi-spot setup. In addition, in this experiment, we both fault the operations and the operands. Here is a representation of the timeline of these experiments. On the top, you can see all the instructions we want to fault. In this case, the XOR operations we want to change into an addition, and the addition plus 1 we want to change into an addition plus n. To perform these experiments, we need to find the period of the loop, that is to say the delay between 2 iterations of the loop. This time is called T-laser. We also need to find the delay between the raise of the trigger and the first execution of the targeted instructions. This corresponds to the 2 delayed T init 1 and T init 2. For example, in our setup, we find that the period of the loop is around 5,500 nanoseconds, which corresponds to 41 clock periods. I will now talk about opcode change possibilities. To do that, we need to take a closer look on the instruction set, which is defined in the ARM reference manual, a document easily found on the internet. We find that the operation with the lowest weight opcode is the end operation, so it will be our starting point. With one laser, we can change the instruction into 4 different instructions. For instance, we can obtain a XOR or a logical shift left operation. We can obtain 6 more instructions as an addition with carry or a logical shift right with 2 lasers. 3 spots allow us to obtain 4 more instructions as a multiplication. And the last one with all the spots, which is a move not instruction. Here you can see all the arithmetic and logical operations of the instruction set. So if the source code contains an add and operation, we can change it to the operation of our choice. In addition, we can also change the value used by these operations. You can find several videos of demonstrations on the YouTube channel of the Uber Laboratory if you want more demonstrations. So as a conclusion, we reviewed why one single spot setup is limited. We also present a new 4-spot laser fault injection setup that can overcome these limitations. And we show that there is 2 new possibilities of fault. This extension of the data collection fault model allows future works to focus on the new attacks on security and cryptographic algorithms. For example, we can find a first application with post-quantum cryptography, and in particular the classic Michaelis crypto system. Thank you for listening. I would like to thank all the partners of the project, which are Alphanov, Therma Group, IDEMIA, ST Microelectronics, and BPI France. If you have any questions, I'm here to answer them.
Thank you for Are there any questions from the audience?
You hear me? Yes? Okay. So I would like to ask you to comment a little bit on how much you can independently position the 4 different laser sources. So how far can you move them apart or together? How exactly does that work? So from the schematic of the setup, kind of what you show is that, I mean, they all go through the same optical path.
Yeah.
So how do you manage to position them in different places?
The 4 laser sources are controlled independently. So the only limitations is the field of view of the camera, which depends to the objective lenses we use. So for example, if we use the objective lens times 20, we can see 500 micrometers of the chip, and the minimal spot diameter is 2.2 micrometers. So we can place the 4 spots in the.
Yeah, but how do you position them? How do you say I want spot 1 to be here and spot 2 to be here, if they come to the same optical path?
The soft is delivered with a setup, and we can. In fact, I don't know how the other spots are placed in this chip.
No problem. We talk later. Thank you.
It's possible.
So you listed a couple of spot diameters and 1.5 watt laser. Do you have some experience how many watts per micrometer or other area unit do you need with different types of technologies? or have you only tried one particular chip? Because as feature sizes get smaller, there's sort of less reception area, and therefore I would expect that you need higher power densities.
It's true that in fact, if the technology becomes smaller, we tend to target multiple bits, but in this case we perform monobit faults, and it has not been a problem for us, and I don't know.
Okay.
I think there's one question.
Right, we have one question online, and that is, the sources have two different wavelengths. Is this due to some physical constraint or for diversity?
We need two different wavelengths because of the liquid mirror, which can only combines beams of two different wavelengths. If we use more than 4 laser sources, it will have optical power loss in the trajectory of the beams. Can you repeat the question, please?
Yeah, sure. The sources have two different wavelengths. Is this due to some physical constraint or just for diversity?
These two wavelengths have been chosen because the silicon is transparent for these wavelengths. But with only one wavelength, we can only have two spots, two laser sources. With 4, we need to have two different wavelengths in order to make the light go to the chip. I'm not an expert in optics, but
yeah, the question writer thanks you a lot.
Are there any other questions from the audience?
My question is, the memory addresses, you showed a figure where there were the 4 laser spots and you were changing bit non-continuously. My question is, the address of the memory could be randomized to avoid this effect that you showed linear shots in the memory, like you said, like you showed, or not?
You talk about this slide? Okay. This one?
This one, yes.
The instructions are stored in the flash memory, and the bits are stored in the order of the instruction. The only change that can happen is the instruction is aligned or non-aligned. But all the bits of the instruction are stored in the order one aside each other.
Okay, thank you.
Okay, since we are running out of time, I would say let's thank the speaker again. And now we have the second talk in this session, which is entitled complete practical side channel assisted reverse engineering of AES-like ciphers. And the talk is actually given by Andrea Caforio. Yeah, the stage is yours. Okay, cool. Hi, everyone. Welcome to my talk about the paper Complete Practical Side Channel Assisted Reverse Engineering of AES-like ciphers. So my name is Andy, and this is a joint work with Lotti Bolli and Subek Bonik from EPFL, Switzerland. So maybe to start, a little motivation why reverse engineering could be interesting. So in the contemporary canon of cryptographic literature, the use of undisclosed algorithms has pretty much been discredited. But if you go into more commercial or military domains, they're still in widespread use. So a good example could be, for example, pay TV systems, or more commonly GSM. And unfortunately, at times, obscuring a rational source could serve a more sinister purpose. So a good example in this case were the Russian block ciphers, which were published with a very doubtful rationale. Or more recently, at this year's Eurocrypt, the case of GA1, which was the encryption algorithm of 2G, which was shown to be, or to have been backdoored. So in this talk, we're interested in reverse engineering hidden structures of AES-like constructions by leveraging side channel observations. This is commonly known as a SCARE, as a side channel assisted reverse engineering attack. So I will shortly introduce what we mean by AES-like construction. Okay, first maybe a little history of reverse engineering in the field of cryptography. So the first practical SCARE was proposed way back in 2003 by Novak, and it targeted the two hidden S boxes of the A38 encryption algorithm of GSM. This was only partial, and then it was later improved by Clavier to recover the full contents of both S boxes. And then later on, quite a few years later on, there was a first theoretical SCARE of AES-like constructions with secret subbytes, shift rows, and mixed column functions, also by Clavier. And independently, in the same year, Rivin and Roche proposed a general SCARE of generic substitution permutation networks. So it's really important to mention here that none of those papers or none of those attacks are actually practical attacks. So all of them are only based in theoretical simulations, which are very hard to replicate in practice. Really, the first practical reverse engineering attack was by Yap and Bazin on an 8-bit processor, and they managed to recover a bit more than half of the 256 hidden AES S-box entries. So in this work, in our work, we actually show, or we demonstrate the first practical side channel assisted reverse engineering procedure for the full description of unprotected AES-128-like ciphers that use hidden or undisclosed subbytes, shift rows, and mixed column functions, and we practically verify them on both 8-bit and 32-bit architectures, namely like an 8-bit ADR and a 32-bit STM that were mounted on a chip whisper for gathering some power traces. More specifically, our attack follows the side channel assisted differential plain text attack methodology, SCATPA. So this kind of methodology fuses the tools from differential power analysis with the strategies or the algorithm from conventional differential cryptanalysis. And then our attack proceeds in 4 steps. First, recover the encryption key, the complexity around alpha times 2 to the 9 traces or encryptions, where alpha is the factor of how many times an experiment has to be repeated to get a stable power trace. We proceed by recovering a partial description of the shift rows, the permutation. Using this partial description of the shift rows, we recover 255 mixed column candidates, and then in the last step, we put everything together and recover the full description of the full cipher. So when I talk about an AES-like cipher, what do I mean? So we say that the AES star is an AES-128-like SPN cipher over the standard Reindl finite field. So it just maps a 128-bit plaintext
with a 128-bit key to a 128-bit ciphertext. We keep the algorithmic structure exactly the same as it is in the ordinary AES. So we start by a key whitening and then 10 rounds of key schedule, the subbytes followed by the permutation, the mixed column, and then we add the round key. Whereas in the last round, we just omit the mixed column. More specifically, in our undisclosed AES-like cipher, the substitution layer, this SBOX, is defined just by some lookup table that maps 8 bits to map 8 bits. Then the permutation layer just is defined by some permutation over the group of 16 elements. So this just shuffles the 16 state bytes of the intermediate state. And finally, the linear diffusion layer, the mixed columns, is defined by an invertible circulant matrix, where all the elements are from the Reinhold field. Okay, then how is this actually implemented? So we chose a very straightforward approach. Specifically, we're actually in our attack only interested in the implementation of the add round key and the substitution layer, and we don't care about how the permutation and the mixed column layer is implemented. And specifically then for the add round key and the substitution, we implement them very simply in a byte-based way. The round key just loads the plaintext, loads the key, adds them together and stores them back. And similarly, we do something similar for the byte substitution. All right, but then maybe the attack is very technical. It introduces a lot of notation. So just as a little compression, for the remainder of the talk, we denote by B just an intermediate state bit. So for example, this would be the first 0 state bit after the first add round key, and so on. And then, for example, this would be the 9th state bit after the permutation layer of the first round. Okay, and what is actually for the leakage model? Leakage model, we also chose, or we opted for something very standard. So it's common knowledge that in differential power traces of an unprotected computation exhibit a strong correlation with the Hamming weight of the underlying variables. For example, this could be due to a bit flip or bit flips during register writes, or for example, when values are placed on a serial memory bus. So we say that the E-bar of an intermediate state byte is an average power trace from acquired during the computation of this byte. And I think this is all you have to know to understand the rest of the attack. And this has really just a very simple application. So by abuse of notation, we say that if a power trace consumes or is higher or consumes more power than a different one, and this can only happen if the underlying Hamming weight of this value is higher than the second one. And we assume we can do this after the add round key and after the subbytes. And this can be verified on very commodity hardware on any kind of microcontroller. These samples have been taken on the STM32. Here we really see that if the Hamming weight of one value is higher, then you get a significant spike or some significant correlation in the differential power trace. So then, using this leakage model, it's really trivial to just recover the encryption key during the key whitening, and this we can do by any kind of attack you can think of. It really works. We chose a simple one. This can be done in roughly 2 to the 9 encryptions, and such an attack, since we can recover the value of a key, then it's also possible just to recover the Hamming weight of any value. And for the remainder, for simplicity, we would just assume that we can recover the Hamming weight of individual bytes after the first or after the round key addition of the substitution bytes with roughly 2 to the 8 traces. Okay, and then finally, what is actually SCAPA? So this correlation between the Hamming distance or the Hamming values of two values and their respective power consumption really implies that any plaintext differential that has been introduced into the cipher or that diffuses through the rounds incurs some discernible differential power trace. And this fusion of differential power analysis and traditional differential cryptanalysis is not a new idea, but it's a relatively recent idea, and it was first deployed by or proposed by Breyer in an attack on Pratt in 2018. In our case, we say that a differential, or we say that by small delta of a state byte is the indicator function that signals whether a state byte is differentially active or not. So it's a black square. We say it means that the ith state byte after the function f of the jth round is differentially active. And the same thing we can say for entire state columns with big delta. Okay, so just as a reminder again, how does our attack proceed? So first we recover a partial description of the permutation. Namely, we recover it up to internal column permutation. Then using this in the next step, we recover 255 candidates for the mixed column. So 255 candidates for this circulant invertible matrix. And then for each of those 255 guesses, we identify a corresponding substitution box. And finally, we can test each one of them with a test encryption to filter out the correct candidate. So let's start with the easiest step, namely the recovery of the permutation layer. So a simplistic approach would be to recover the full description of pi through SCAPA would just be to introduce a plaintext differential in the ith byte, and then check whether at what position it is, the differential spike is observable after the first permutation layer. However, this is not really might be too simplistic, because depending on the implementation of how the cipher is actually what the cipher shows, that could be that the permutation layer and the mixed common layers are computed together. And then it's not really possible to discern such a differential spike. It could also be that individual bytes of swaps of this permutation layer are executed in a different order, maybe for efficiency reasons, or maybe even as a part of a countermeasure. And finally, there could be eventual fixed points, and they might not be executed, which would shift the entire thing and make it very hard to discern some clear differential parsepath. What we instead opted to do is we want to observe differential peaks during the Rankine addition of the first round, or of the substitution layer of the second round. Namely, we introduce a differential at the beginning, it diffuses, and after the first permutation layer, it ends up at at a different position, possibly. This different position, with one active byte after the mixed column, this will diffuse into entire column. And then here we do our side channel observation, and we see at which column is actually differentially active. This is relatively simple. This will give us immediately one dimension of the permutation, and it will tell us to which column a byte is shifted after permutation. But it doesn't tell you at which position within the column the byte ends up. This is what I just said, and then this is how it would look like if we actually took the power measurements. Here we see that here we measure the substitution layer of the first substitution layer of the second round, and we see that in this case the first column is differentially active while the other three are not, or similarly the second column is active while the others are not. So this is clearly discernible. How complex, or what do we have to do to this? Well, we have to repeat this for each state byte, and for each state byte we need 2 average power traces, so in total we need like alpha times 32 traces in total. So now let's move on to using this partial one-dimensional description of the permutation layer to find 255 candidates for the mixed column. Remember, this is our undisclosed secret mixed column matrix, and we want to recover 255 potential candidates. So here we again start with a different differential. Namely, we are interested into differentials that activate 2 bytes in the same column. Let's say in the first column after the permutation layer of the first round.
And then we hope to observe something. Namely, we hope to observe that these two active bytes diffuse into 3 active bytes after the mixed column of the first round. This happens with some probability. This is the occurrence we hope to observe. So let's say that D0 to D3 are the differentials of in the first column after the permutation layer of the first round. We again check the add round key of the first round and the substitution box or the substitution layer of the second round for spikes to see if we actually have such an occurrence, namely that we want to have 3 active bytes and 1 inactive bytes in the first column. But there's a problem because we don't really know, since we only observed the power traces after the mixed column has already been computed, and we don't really know the internal permutation of the permutation layer. We don't really know which actual bytes are active here. So for this, we have to introduce some more notation. So let the 4 tuple U be the indices of the bytes that get mapped to the ith column of the first round. So for example, U0 to U3 would be the indices that map bytes to the first column. And since we already know 1 dimension of the permutation layer, there can only be 4 factorial or 24 candidates, namely all the different permutations of these 4 tuples are unknown to us. So now assume we lock one of those 24 possible choices. We proceed like this. So first we fix plaintext bytes, PU2, P prime U2, and PU3 and P prime U3 to some value. Just make sure they're equal. And then we find some plaintext bytes PU1 and PU0 and PU1 for which the Hamming weight after the substitution layer of the first round is 0 for both of them. Similarly, we find a plaintext byte P prime U0 that gives us a Hamming weight of 8 after the substitution of the first round, which is akin to a differential 255. So this would mean that this D0 would be 255. And then we just iterate over all P primes U1 in this set and check whether there occurs 1 inactive byte. If this is the case, we can build up a relation, because now we know that D0 is 255, D1 is some unknown value x1, and the others 2 are 0 because we have fixed them to the same value. This gives us a relation depending on the mixed column. And then we can just repeat this game multiple times. So we can repeat it for different axes at different positions. And for each one, we could get a new relation. We did this 10 times to get 10 relations. And then using those 10 relations, we can build a system of equations. And then it's possible to prove that given the system of these equations, and knowing that we have correctly guessed the permutation of the indices, then it's enough to just recover the Hamming weight of those unknown x values, and it gives us 255 candidates of n. This is nice, but we have to correctly guess those 4, or the one of those 24 permutations. So what about the others? Maybe first a visualization again. So we start with 2 differentials. And we want one of them to be 255 and some unknown differential. And then we hope that after the mixed column of the first round, it diffuses to 3 active bytes in the same column. If you observe something like this, we know we have a relation. And then we repeat this. So we can start with this one, and then we can swap them, and then we can also look for an inactive byte, not in the first byte of the column, but in the second byte, and then in this way we just get all the relations. But again, there's a problem because we don't really know the actual permutation of those 4 indices, of this 4 tuple. Fortunately, for 20 other incorrect guesses of this 4 tuple,
our filters do not yield any real solution. So we can prove, it's provable that for 20 of those guesses, we will never get a solution for M. However, for the 3 remaining guesses of this 4 tuple, namely of those which are just a rotation of the individual rotation of the correct choice, we get row-rotated versions of M. But this is not really a problem, because since this is just a rotation of the correct guess, and M is itself just a row-rotated version of the correct M, they're all algebraically equivalent. So we don't really know, we have to know which of the 4 guesses it is. The only thing that is left to do, we have to repeat this for each column. We guess we do the same thing for each column, and then we just take those guesses which yield the 255, the same candidates for M. So how complex is this? So to recover the 0 Hamming weight of those 3 values, we need to repeat this 3 times. So it's 3 times 2 to the 8. Then we need to find 3 times the Hamming weight of a value 255 after the substitution box, same complexity. And then we have to find, and such a convergence or such a diffusion has to happen where there's only 1 inactive byte. So this happens with roughly, again, 2 to the 8 with probability 1 over 256. So, and since we have 10 steps, we repeat this 10 times. And then, of course, we have to repeat this for each column 24 times. Putting this all together roughly requires roughly 1 million traces to recover 255 candidates of the next column. And this really just segues into the last step of the attack. And here we want to actually recover everything together, since we still don't know what the substitution or the SPOC looks like. So here we are interested in a different kind of diffusion of a differential. Namely, we're interested in a diffusion where all bytes in a column are active after the permutation layer of the first round, but then after the mixed column, this converges to a single active byte. And this is actually not a new idea. This has been used in this very particular convergence has been used in a different Scott-By attack, namely on partially masked AES by buzzing. In this paper, they prove that for this to occur, roughly, we need on average roughly 2 to the 11 or 2 to the 12 encryptions. So now it's pretty easy to see that mathematically such a conversion can only happen for a specific set of differentials, namely differentials of this form, where E, F, G, H are just the coordinates or the elements of the inverse circulant matrix, and lambda is just a value in the field. Okay. Okay, so knowing this, we can proceed. So now the first step involves just finding some plain texts that give you a 0 value after the substitution layer of the first row. This would simplify this equation system, since this will be 0. We're left with this. And now we just recover the Hamming weight of each of those values, using observations of the at round T of the first round or the substitution layer of the second round. We recover the Hamming weight of each value. And this gives us some Hamming weight fingerprint. And then this fingerprint we can look up in some pre-computed table and see if we get a unique response. So we calculated that on average, the lookup table contains roughly 200 unique entries. So if we are lucky and hit a unique entry, we recover 4 elements of the S-box. So for the complexity, so the first step, so finding those 4 0 images requires 2 to the 8 encryptions. And then, of course, we have to wait until we observe a convergence. This happens of roughly as seen after 2 to the 11 encryptions and times multiplied by some factor beta, which is the inverse probability that the unique Hamming weight fingerprint is found in the pre-computed table. So one can prove that if E, F, G, H are chosen uniformly at random, then beta is roughly 1.3.
That's not too bad. And since in each step we only recover 4 elements, we need to repeat this 64 times to recover the full description of the substitution box. So putting this together would roughly amount to a bit more than, let's say, 2 to the 18 encryptions. And then all that is left to do is just test whether for this candidate of the mixed column, the substitution box yields a valid ciphertext. If not, we just repeat. Yes, this concludes the attack. So where to go from here? So of course, I was glossing over the fact that, or we made our lives a bit simple by choosing the mixed column as circulant. But you could also imagine that the mixed column is entirely randomly chosen. So this would complicate matters a little bit. Oh no. Okay. I'm sorry. That's this. I can't go back. All right. Then, of course, everything we did was on unprotected implementations, but usually in the wild you find protected implementations, so this will again complicate matters significantly. And then finally, of course, if you, for example, look at standardized implementations of AES, they usually use a T-table, so to compute the substitution layer and the mixed column, the shift rows in one with multiple table lookups instead of like having them separately computed. This, of course, would not work in our attack because for the SBox recovery, you need to find the Hamming weight of the SBox of the first round. So since that's, if the SBox were implemented together with the mixed column, this would not really work anymore. And I guess this is all I have to say. Thank you very much. So thank you for an interesting talk. Given that we really are quite far out of time, if there's one quick question, maybe we can take it here. Otherwise, I would totally take it offline, and then we directly continue with the next session, the online session. Okay.
Yep, exactly. So now CARDIS will really become a hybrid conference because we will start with the online session. It will work with the usual approach that was taken by other online conferences in the last 2 years. So we will have a 5-minute short presentation of a paper, and the full video, full presentation can be watched on YouTube. It's already linked in the program, so if you want to know more, you can have a look there. The next session will be chaired by Tobias Schneider, who is hopefully already with us. Maybe you can say hi.
Yeah, can you hear me? What? Cannot hear me?
Maybe you can say hi again.
Yeah. Hi. Can you hear me now?
Yes. It does not seem to work. So, now it works. Hi, Tobias.
Hi.
Hi. Cool. Then, yeah. So maybe you can introduce the next session then, and also everybody in the room, you can ask questions. So the microphone will also be somehow fed into the stream and is available to the online participants. And yeah, without further ado, Tobias, yeah, the stage is yours.
Yeah, thanks, Thomas. So yeah, welcome to the third technical session of CARDIS. We will hear about 3 papers related to hardware security. Maybe to repeat what Thomas just said, this is the first online session. So each paper will be presented in a 5-minute pitch with some subsequent Q&A. Yeah, online participants can ask questions over this CARDIS chat on MetaMost, and I was told, yeah, that there's supposed to be a microphone. Not sure if I can see it, so if you have a question, just make yourself noticeable that we know it here in WebEx. We will have a joint discussion session after all the paper pitches. So if you later come up with a question to an earlier paper in the session, do not hesitate to ask it. So there, then I think we can already start with the first paper. Vincent, can you maybe share your slides?
Do you hear me?
Yes.
Yes, okay. Oops, share.
Okay, so the first paper is called Fast Calibration of Fault Injection Equipment with hyperparameter optimization techniques by Vincent Werner, Laurent Mengot, and Marie-Laure Potet, and Vincent is going to give the presentation.
Okay, so do you hear me? It's okay? Yes. So
Yes.
Welcome to this presentation. I'm Vincent Werner, I'm a PhD student from the CEA Grenoble and Verimag, and today I will talk about fault injection and how to calibrate fault injection equipment with optimization techniques. So let's start. So first, how do we inject faults? Well, we can use any technique that will alter the microcontroller environment locally or globally, and the most popular techniques are laser fault injection, electromagnetic fault injection, and power glitch. And once we have chosen one technique, we have two things to do. So first, we need to know when to inject faults. So for that, we must find vulnerabilities on the target application. And to do that, we can use binary analysis, for example. But this is not the scope of this presentation. And the other thing we have to do is to calibrate the equipment, that is, find the best settings to inject fault. And each fault injection technique has a specific parameter space, and depending on the complexity of the parameter space, the difficulty to find the best settings is not the same. So, for example, to do power glitch, we must find the amplitude of the glitch and the duration of the glitch. So usually the parameter space is small, and we can identify easily the best settings, even using a brute force approach. But with electromagnetic fault injection, usually we have 5 or 6 parameters to find, and as a result, the parameter space is much bigger, and consequently, we cannot use a brute force approach. So for this situation, we need techniques to identify the best settings. And to do that, we can either reduce the parameter space by finding the most interesting regions of the chip, which is again not the scope of this presentation, or we can explore the parameter space more efficiently using optimization techniques. So, for example, we can use the grid search. So this popular technique is a semi-exhaustive search on a predetermined range of values. We can also use the random search, which is slightly better than grid search, but still inefficient. Both techniques are only effective with small parameter space and spend too much time on poorly performing configuration because previous results are not taken into account. Instead, we can use genetic algorithms. These algorithms are based on evolutionary theory and have been already applied to electromagnetic fault injection and power glitch techniques. They are better than random search or grid search and easy to implement. However, there are two main limitations. First, we have to adjust many hyperparameters, for example, the number of generations, the selection strategy, and so on. These hyperparameters strongly influence the final results. And the other limitation is that genetic algorithm can suffer from premature convergence. That means that we can be stuck into a local optimum, which is not good. But hopefully, new optimization techniques have been proposed over the last decade, such as bandit algorithms and Bayesian optimization. These techniques are already used in machine learning to optimize machine learning models, but they are not applied to fault injection in order to optimize the fault injection equipment. So in the video, we'll see that the bandit algorithm and Bayesian optimization can be successfully applied to fault injection. We will present these techniques and we will evaluate them on 3 different 32-bit microcontrollers. And finally, at the end of the presentation, we will do a quick demonstration on a real-world example using Bayesian optimization. So far, we talked about optimization techniques only, and we didn't talk about methodologies yet. And one interesting approach has been proposed by Karpi in 2013 to split the optimization problem into 2 steps in order to identify the best settings independently of the injection delay. They use a target application for both steps, but with the target application, so it can be difficult to observe fault effects and to completely ignore the injection delay. So in the video, we will present our two-step optimization approach based on characterization tests, which are small programs designed to maximize fault propagation in order to identify the best settings more easily. So to understand how we can use recent optimization techniques combined with characterization tests in order to speed up the equipment calibration, don't hesitate to watch my video. So thank you for your attention.
Yeah, thanks, Vincent. Are there any direct questions at the moment in the room? Because I don't see any in the chat.
No, right now there are no questions from our side here.
Okay, then let me just ask a quick one. So in your experiments, you looked at like a voltage grid which had like 9 parameters.
Yes.
Did you check if all 9 parameters were equally important for the quality of the injections, or were there some that you can ignore?
So let me share my screen again. Share. So basically, yes. So this is the setup we use in the experiment. So I don't know if you see my screen, but so this is the setup we use. So yes, we have 9 parameters. So 8 parameters for the glitch waveform, and the last one for the duration. Yeah. So to answer your question, I don't know. I didn't check. So for me, each point is important, and the glitch waveform depends on the target you use. So for example, so we try with different microcontrollers, and the glitch waveform was different for the Cortex M0, for the M3, and the M4. So I cannot say which voltage level, which point is more important than the other.
Okay, so your methodology does not inherently support to give like a value to each parameter, right? It's basically just a black box.
Yeah, I mean, yes. For me, yes, each point is the same for me. There is no way to put on the first one, for example. Yeah.
Okay, thank you.
You're welcome.
Good. Then let's maybe continue to the second talk of the session. Christoph, can you share your slides?
Yes. And do you see my slide?
Yes.
Okay.
So the second paper is called Trace-to-Trace Translation for SCA by Christophe Geneviève Métard, Annelie Heuser, and Benoit Girard. And Christophe is going to present.
Yes, thank you. So hello, my name is Christophe Geneviève. I'm a PhD student in capsule team at NURN. I work on machine learning with side channel analysis with Annelie Heuser and Benoit Girard. And I will introduce a work called Trace-to-Trace Translation for side channel attack. So first, a little introduction about a side channel attack. Imagine you have a cryptographic algorithm which running on a device. This cryptographic algorithm take as input a plain text and produce as output a ciphertext. During the execution of this cryptographic algorithm, the device will provide different side channels such as electromagnetic emission, power consumption, timing, sound, or heat. These side channels are directly linked to the internal state and processing of the device. In your work, we focus on electromagnetic emission and power consumption. First, in your case, an attacker can capture several EM trace and power trace and use some mathematical tool such as the correlation to guess sensitive information. So depending on the capability of the hacker to acquire a certain amount of trace, it can proceed in a different way. In your case, we focus on the regular deep learning based side channel attack. So this attack consists to use two datasets, a profiling set and an attack set. The profiling set is labeled. That means for each trace we know the corresponding key. And the attack set is unlabeled. That means for each trace we do not know the key. The profiling set generic comes from a clone to the device to target, and the attack set comes from the device to target. So we use the profiling set to train a network, and after the training of the network, we use the attack set to guess the key. In our previous work, we have observed a different thing. First, some channels are easier to attack than another. For example, power consumption is easier to attack than electromagnetic emission. We also have some devices that are easier to attack than others. For example, some devices link more information than the other. And finally, some implementation are easier to attack than another. For example, implementation without countermeasure is easier to attack than implementation with countermeasure. So our goal is to investigate if GAN can translate trace from one domain to another, which is easier to attack. So there exists some related work. They have the work of Wu and Pisek that investigates the autoencoder capability to denoise and remove the effect of various hiding countermeasure. So they use an attacker as preprocessing operation, and they also use ASCAD as a database. So ASCAD is a database that aims at providing a benchmark reference for the CSI community, and it was proposed by the French government. So in our approach is different because we do not require mostly trace, but just trace easier to attack. So the context is the following. We have a device to target. We can extract from this device a profiling set and an attack set. And we also have another data set. We assume that the other data set corresponds to the domain B. So the domain B is easier to attack than the domain A, and the domain A is described in red. We also assume that the dataset from domain B and A are a parallel dataset. That means these two datasets share the same intermediate target value. And so in this context, the attacker can ask how he can attack this device. So we develop two additional attacks in addition to the regular deep learning attack. So the first is a translate attack. So the goal of the translate attack is to use the dataset from domain B to pre-train a network and use the dataset from domain A to learn again to translate trace from domain A to domain B. After the training of the GAN, we use the synthetic attack set and the pre-trained network to guess the key. The other additional attack is the pre-trained attack. So the pre-trained attack consists to use the dataset from domain B to pre-train the network and directly the attack set from domain A to guess the key. So in our contribution about the GAN network, we adjust and fine-tune two GAN architecture, so CGAN and Pix2Pix. CGAN was originally designed for the speech enhancements, and Pix2Pix was originally designed for the image translation with parallel dataset. So we fine-tune these two networks for the side channel attack. And we investigate two scenarios. So we have investigate the translation from EM to power and the translation between a device. So in this paper, we successfully translate trace from EM to power and also translate trace between a device. We observe that when regular attack fail due to a lack of data and if a parallel dataset is available, trace translation help. In photo work, we want to investigate if GAN can translate protect trace into unprotect trace. And we also want to see if GAN can work with unparalleled dataset. So if you want more detail, you can ask a question or I invite you to watch a whole video. Thanks.
Yeah, thanks, Christoph. Are there any questions from the audience? I assume not. Then let me ask one. So I watched your video and it actually was quite interesting, but do you know what the limit of this translation is? Could you take audio measurements and translate them to power?
Sorry, can you repeat?
Yeah, I mean, in the paper you translated EM to power, right?
Yes.
Would it also work from audio or temperature to power?
We have done try to translate other scenario. We just yes try EM to power, and for the case of the translation between device, it was power to power, but we have done try with other sub channel.
Okay, that might be interesting as future work.
We also have a local question here.
Okay.
Is it okay? Can I talk? Okay. In the case of power and EM, how does your work compare to, if I remember correctly, there was a paper a few years ago about sensor fusion, when you would record both the power and the EM of the same implementation as it was running, and then using the combined information to recover. So how does it compare? Do you gain by translating, or is it just the additional information that you have 2 times the trace that helps you?
Sorry, I have the sound was not high. Can you repeat, please?
Okay. The question was about the comparison with the previous work that was called sensor fusion, where they were recording both the power and the EM consumption of the target as it was running, and then combining both to recover the key. So my question was, how does your work compare? Do you gain information by using this translation, or do you just gain information because you have more data, basically?
Okay. We have tried to compare with the, like I say, with the regular deep learning approach. So, for example, when we translate EM to power, we just compare the translation with the EM, and if we translate to power, we see that the translation from EM to power has a permit to have more information.
Okay. Okay. Well, we can we can discuss it later. Maybe it's
okay. Yes.
We have one more question here.
Okay.
So another translation technique that has been widely used, linear discriminant analysis, is specifically targeting, trying to find a transform that maximizes signal-to-noise ratio. Have you compared it with approaches that go specifically for maximizing signal-to-noise ratio rather than just emulating another sensor type?
Yes. So during the fine-tune of the GAN, we have selected the best architecture of the GAN based on 2 things. The first was maximized of the signal-to-noise ratio, but we have also selected the GAN parameter based on the efficiency for the attack.
Okay.
Does this answer the local question?
Yeah, I saw a short nodding. Yes, okay. It did answer the question. Thanks.
Good. In view of time, let's continue to the third paper, but if you have any other question to the second paper, we can come back to that at the end. So Stephanie, can you share your slides?
Do you see my screen?
Yes, perfect.
Okay for you?
Yeah. Yeah. I mean, I just want to intro. So the third paper is called Laboratory X-rays Operando Single-Bit Attacks on Flash Memory Cells by Laurent Mongault, Stéphanie Anson, Manuel Simon, Luc Salvo, Jessie Clédier, Pierre Lucie, Emeric Billiard, and Jean-Luc Reynard, and Stephanie is going to present.
Thank you for listening to me. So my name is Stéphanie Anson. I work in Leti ITSF in Grenoble-Alpes University. This work is called a Laboratory X-ray Operando Single Bit Attack on Flash Memory Cell. And this was done by all the team you have said from Grenoble. Part of them work in Leti ITSF laboratory, and part of them work in CMAP laboratory in Grenoble-Alpes University. So, so the Leti ITSF laboratory is the Information Technology Security Evaluation Facility. And this laboratory is doing attacks on integrated circuit for security evaluation. And this laboratory gives a report evaluation to a certification organism in Paris, which his name is ANSI. And the certification organisms gives a certification or not to the industrial client, which give him the access to the French market. A part of the attack can be electromagnetic observation, electromagnetic fault injection, FBI, or laser attack. But lasers are limited in focalization and technology node device. That is why we have done an investigation on X-ray attack with nanofocalized X-ray beam with a synchrotron. And this allows us to obtain the best paper at the CHESS conferences in 2017. Our X-ray beam is focalized to 50 nanometers, and with the synchrotron, we have done localized single bit attack on flash memory cell and RAM memory cell on 350 nanometers technology node and 45 nanometers technology node. Today, I would like to present you my work on flash memory cell of 350 nanometers technology node with the X-ray from laboratory sources. This is part of the MITIX ANR project, where there are 4 laboratories, the Leti ITSF, the CMAP laboratory, the TIMA, and the ONERA laboratory. So for the experimental results, we start from a quite complicated preparation. We take an ATmega 120N pin, and we use a milling machine in order to prepare the backside device. We reach the integrated substrate, integrated circuit substrate, and we do a tungsten mask deposition with a focused ion beam. We make a hole in the tungsten mask deposition above the flash memory block. And we do an alignment of the lead mask and the tungsten mask deposition in order to see the pinhole. And we use an experimental setup, which is an X-ray EasyTone nano sources with a molybdenum target. And this X-ray sources from a laboratory is diverging. So we do we use a superposition of lead and tungsten mask in order to focalize the beam. For the result, after 520 seconds, we have several bit fault attack. And until 14 transistors are fault before the column faults. And we decide to simplify the experiment. So we start from the ATmega device, and on the front side, we glue a lead film, which thickness is about 50 micrometers. And we make hole with a focused ion beam on this lead film above the flash memory block. And you can see with the X-ray transmission in pictures that the hole are as small as possible and cross the lead film. With the X-ray sources, we try to simplify the setup, and we use a tungsten target instead of the molybdenum target. And you can see on the results that in each hole, we have a single bit fault attack, which is a random single bit fault attack in the hole. After, there are several bit fault attack before the column fault attack. So to conclude, we have used the conventional tungsten target X-ray sources for managing the backside and the front side single bit attack on flash memory at 350 nanometers technology node. We can use a removable lead film which can be prepared once with a focused ion beam and used to perform several attacks on several devices. And for the outlooks, we have to use a removable lead film and on more advanced technology node component and do random single bit flash memory attack. We have to perform a localized attack on one specific transistor with the X-ray laboratory sources. And we have to investigate the possibility to perform attack in glue logic on the SRAM using both synchrotron and laboratory X-ray sources. Thank you for listening to me, and I'm pleased to answer your questions.
Yeah, thank you, Stephanie. Are there any questions in the room?
Yes, we do have one. Give us a second.
How do you align the holes in the foil with the FIB? Because you can't see through the foil, you can't see the structure, right?
We have an infrared camera in the focused ion beam, and we see the flash memory block, and we do the tungsten deposition on the back side of the device above the flash memory block.
Okay.
So we do a hole in the tungsten deposition above the flash memory cell.
Okay, thank you.
Is it answering your questions?
Yes, yes it did. Thanks.
Okay, maybe let's open the room for questions on all the 3 papers. Are there any questions that you have maybe to one of the earlier ones?
Maybe we can first give all the authors one round of applause.
You have to tell me when it's on.
The local participants always don't know whether they should give applause or not because they don't know whether it can be heard by you. So, yeah. But now, please go for questions.
Okay. So if there are no local ones, let me maybe ask one to Stephanie. So you said you observed random faults, so it was not like setting or resetting, but it was different every time?
No, it's not the fault which is different, it's the position, because we have a hole and we have several memory cells in the hole of the tungsten and the lead mask. So we make a first single bit fault in the hole, but when you wait for several hundred of seconds, you have several bit fault in the hole because the size of the hole.
Okay, but the faults itself are always then, I guess, set or reset.
It's a flash memory erase.
Okay, erase. Okay.
And after, if you wait, for example, 1 minute, 1 minute or several minutes, I don't have the table here. You have a column fault, which is the permanent conduction of NMOS transistor, the N-access transistor. The flash memory.
And this is the one that you can reverse with heat? Did I understand correctly?
Yes, you reverse both. You reverse by heat. Yes, yes.
Okay. Any questions in the room?
Does not look like it.
Then let me ask one to Vincent. So for the bandit approach, you mentioned that you have multiple injections per configuration. I guess it makes sense to maybe increase the confidence in this configuration, right? Can you maybe give some intuition how many injections you usually need to get the good confidence that the configuration is good or not?
Well, I suppose the process is iterative because after, for example, 10,000 fault injection, you get a good settings. Then you test these settings on the real target application and you try to do the attack. And if you cannot, then after well, you can repeat the process and try to find another settings. But usually, for the real world example I show in the video, we can just do 5,000 fault injection, and usually the configuration that is found is okay to do the attack.
Okay. And yeah, I think you also mentioned that you want to use it for EM and laser fault injection. Can you maybe go into a bit more detail what the challenges would be and how you maybe expect them to be solved?
So yes, we believe that it can be applied to laser fault injection and electromagnetic fault injection because SMAC, so it's Bayesian optimization. SMAC has been already applied to solve hard combinatorial problem solvers that have, for some, have more than 73 parameters, so a really big space, and SMAC can identify the settings. So we believe that SMAC can also be applied to electromagnetic fault injection. But I think there will be some issue with electromagnetic fault injection with the spatial displacement of the motors because, for example, when with grid search, the movement with the motors is always the same, and there is no brutal acceleration. But with SMAC, because it's a bit more random, so I believe we have to calibrate the motors to not have shake. I don't know how to say. If the motor is not well calibrated, the test bench will shake a little bit, and the result will be bad because we will move the motors very fast in all the position. And when we do a grid search approach, usually we do always the same displacement, the same movement. So yeah. So we
So it would add maybe some extra time that you need to wait until everything is stable.
Yeah, maybe. Yeah. We will see. We need to do the experiment.
Okay, thank you. Any questions left in the room? I don't see any online.
No, there are none here in Lübeck either.
Okay. Then let's maybe thank all the speakers again. There was some applause now. And this concludes the technical part of today. Yeah, and I think just the last thing that is left is to wish the people that are actually attending physically a nice conference dinner.
Thank you, Tobias. Yeah, just a short announcement. Exactly. So for today, the technical part of the conference concludes. We will continue tomorrow. For the people that are participating online, we will continue tomorrow at 11:30 with the technical program. So thank you for the online participants. For the ones that are here local in Lübeck, we will have the conference dinner tonight. We will have it at the restaurant Schiffergesellschaft at 7:30. That's in the city center, so we will have to walk about 15 minutes. So I would like to invite the people who do not directly want to go there that we meet in the lobby of the hotel at 7 p.m. and then we can walk there jointly. And if you are, otherwise people on site for tomorrow, we'll start at 9:15 for the social event. We will have a city tour, and yes, we'll meet in the lobby of the hotel at 9:15 tomorrow morning to go on the city tour. Right. So either definitely see you tomorrow, and also see you either at 7 in the hotel lobby, so in half an hour, or at 7:30 at the restaurant Schiffergesellschaft in the city center. Thank you.
you.